Vou comentar que o Adro mandou mensagem. Peraí, gente. Alguém pode me dar as informações do meeting agora, por favor? O link do Zoom?
Eu vou te mandar aqui. Eu fui aberto na minha mão.
Manda o link e a senha.
No WhatsApp?
Tentando... Não, pode ser.
Invite.
Acabei de te enviar, Paulo.
A função invite não serve para isso, não?
Deve servir, mas é que eu vou mandar isso. Ok, pessoal, acho que a gente pode começar. And so we switch to English. First of all, thank you all for being here. We would like to describe an initiative that started a few months ago, and the name that we have here is still tentative. We would like to begin to start a new program at FAPESP devoted at the development of quantum information technologies. The people involved with this initial effort are Professor Celso Vilas Boas from the Federal University of São Carlos, Professor Federico Brito from USP in São Carlos, Professor Gustavo Wiederhecker from Unicamp, Physics Institute at Unicamp, Professor Marcelo Terra Cunha from the Math Institute at Unicamp, myself, Physics Institute in São Paulo, USP, and Philippe Cortei from the Physics Institute in São Carlos. This started a few months ago. Our first Zoom meeting was on August 17th. And we've been meeting every week since that first meeting. We split the strategy in two phases. The first phase, in which we wanted to prepare a document in order to convince FAPESP governments that it was worth pursuing the idea. And so we had that meeting on October 28th. Prior to that meeting, we held meetings with people from certain industries, from the private sector, for instance, Petrobras, IBM, Microsoft, and others. I'll come to that later. In those meetings, we made sure to tell people that we had no mandate from FAPESP at that point. So it was just initial contact. Since the meeting on October 28th, we have the mandate from FAPESP to formulate a proposal for this new program. It is far from ready. There's still going to be a lot of effort. Since that meeting, we decided that one of the first things we needed to do was to involve the academic community working in the field in the state of São Paulo. And so we put together this meeting today, and we invited two people who are working with startup companies in France, in the US, and Professor Vanderlei Bagnato, who has large experience working with startup companies and innovation in Brazil. We would like that to set the tone of our intention, which is we are firmly convinced that we are developing state-of-the-art quantum information science in Brazil, also in the, namely in the state of São Paulo as well. But this has to revert to quantum technologies. And so the way to do that is to try and join the community in this effort to make sure that we can find near-term quantum technologies that can be developed and bring revenue to the state. Now, you may have noticed, if you look at the pictures here and the pictures here, that people's hairs have changed a little bit. Notably, Freddy is the one whose hair has changed the most. But also Marcelo, I think, yeah, Marcelo, you also made some changes. Okay. To motivate this and to show why there's such excitement in the world, this is an issue, a special issue of The Economist that was published in March 2017. The Economist is not an academic journal. It is not devoted to basic science, but they had a special number with very interesting and well-written articles on the possibility for novel quantum technologies. In that journal, I think there's a very inspiring quote. There's a lot of excitement in the community, so the odds for achieving success, the odds for building quantum computers, the odds for building quantum information networks are good. The goods on which we build are odd. And so I think this is very inspiring in going forward. We are using all the strange properties of quantum mechanics that we've learned over more than 100 years in order to develop novel technologies. They made an assessment of the annual spending on non-classified quantum technology research in 2015. And we can notice that there was a prevalence of the European Union with about 550 million, the United States with 360 million, China, a world estimate of 1.5 billion euros, and Brazil was here with 11 million. The source for this is McKinsey, and it's an estimate, right, which is essentially for the annual spending. This year, a company called QuINTec made an overview on quantum initiatives worldwide. From 2015 until now, several countries have announced focused efforts on building novel quantum technologies. And this is part of the reason why, we decided to start this. I was personally poked at a conference by Peter Zoller, who said, look, why isn't Brazil starting some quantum initiative? Now, we all know the economic situation in the country. We know the political situation in the country. So at the federal level, to begin something like this right now doesn't seem very likely, but I told him in the state of São Paulo, it was possible to think of an initiative like this. Of course, this was pre-pandemic, and this was also pre all the effort that we had to make as a community to fend off attempts by the state government to lower the budget of FAPESP. Fortunately, FAPESP will have its entire budget for next year. And anyway, we believe that this initiative, if successful, if we are able to launch a program, it will still take us another year because we really want to formulate it very precisely. So if we look at this, there's an estimate of 21 billion in 2020. Many of these initiatives are not for a single year. Some of them are for up to 10 years. But even if we divide it by 10, it would mean an increase from the annual spending from 2015 to 2020 from 1.5 to 2.1 billion. I would say it's more than that because some of these are for 10 years, some of these are for 5 years, as in India. Still, it's a significant amount. And of course, it's very noticeable that there is nothing related to in Brazil. So again, quantum technologies will be developed. They will arrive whether we like it or not. And it's much better if we are prepared for them. So in discussing what are these quantum technologies, of course, since this meeting is targeted at the academic community in the field, I'm not going to spend much time talking about the fundamentals of quantum mechanics, talking about the fundamentals behind each of these technologies. We can split them essentially in three major areas: quantum information processing, quantum computing, algorithms, simulators, development of basic building blocks for these systems. We can look into quantum communications, so secure communications via cryptography, development of sources for that, studies of non-locality and entanglement, usable for teleportation, and a platform of integrated photonics for these technologies. And also sensors, the ability to sense nature with much better sensitivity and precision using different technologies, superconductors, optomechanics, 2D materials, color centers, Rydberg atoms. There's a lot of room here in order to do that. And there are many different possible applications for these technologies, spanning from agriculture, and this is one particular field in which we are very, very interested in because we think we can develop relatively simple sensors, whether quantum sensors, whether quantum-inspired sensors for applications in agriculture. And of course, São Paulo State is very, very strong economically in agriculture. So this will have immediate economic revenue. There's also energy, clean energy sources, energy photosensors. So there's, again, another field. And health. For instance, magnetic sensing is very useful for detecting, for sensing the brain. And so, again, there's a lot of possibilities for the development of these technologies. I would like to add something that we've thought of also, and it's based on a discussion with a partner from Australia. They were developing a spectroscopy method to scan chips where they had quantum dots implanted. And they wanted to do something that would be broad and do it at once. The same kind of technology is being adapted to be embarked on drones and be able to do sensing for agricultural purposes. We already thought that we could ponder developing this kind of technology, for instance, for biosensing or biodiversity sensing, right? And that would be useful for another FAPESP program, which is very successful, BIOTA. I don't have to tell this community that we already have a lot of quantum science going on in São Paulo. And a lot of this quantum science could be applied to technological developments in terms of sensors. We have an effort already in USP São Carlos, chip scale integration in Unicamp, and also we have a small effort in USP, superconducting qubits in Unicamp, studies of quantum thermodynamics, theoretical studies spread out, experimental studies at the Fellow University of ABC, use of entanglement and possibilities in quantum communications. One such possibility that we haven't explored so far is the development, for instance, of quantum random number generators, which are of general purpose, general interest for computing. I'd like to mention just a few breakthroughs. There's, of course, a lot of excitement from the growing and increasing speed in the development of quantum computing. Big companies are now strongly investing in that. And last year, Google had this breakthrough, the demonstration of quantum supremacy using a programmable superconducting processor. We've seen very, very recently an announcement of supremacy from an a photonic setup, but it's not universally programmable, so it's not a universal processor. IBM is also very, very heavily investing in this, and I saw this tweet by Jay Gambetta, which shows the development over 10 years. This is what one superconducting qubit looked like in 2010, and this is their most recent processor with 65 qubits. And of course, there's a coin to show the scale, right? And so this is very, very impressive development over 10 years. IBM put out a roadmap, and they intend to have next year 127 qubits. They project by 2022 433, 2023 more than 1,000 qubits, and sometime soon up to 1 million. So this is a fast developing endeavor. In China, Jian Weipan has been pushing very, very hard, especially for communications. So they now have satellite links in which they can exchange secure keys from China to Europe and in different places in China. So again, this is something that is happening, and somehow we have to be a part of it. In the Economist in 2017, there's this very nice quote by Sir Peter Knight that one of the big challenges for going forward in developing quantum computers is the fact that quantum systems coupled to the outside world very effectively, and decoherence kills the resource for quantum computing. As Peter Knight says, you turn it on its head. If it couples to the outside world so effectively, it's sensing the outside world really effectively. And so there's, for instance, this review on quantum sensing from the Capellaro group, published in Reviews of Modern Physics in 2017. Of course, there's even more recent work. I just like to point out that this is something that is already ongoing here in the state of São Paulo in terms of developing gravimeters. And gravimeters can have very, very interesting applications. Philippe was already approached, for instance, if it would be possible to develop gravimeters to measure, to weigh cargo. Okay. Philippe has deposited a patent for this. I'd like to point out something that has occurred to us even before this initiative, but this announcement from November 23 is something very interesting to develop a quantum X-ray microscope using synchrotron light, right? And to do ghost imaging of biomolecules. Earlier this year with Marcelo Martinelli, we went to the Brazilian synchrotron source, and we are convinced that we should do some serious quantum optics and quantum information in the near future. Again, this is one of the possibilities where we have unique capabilities and that we can build on. This is just a short list of all the different systems and technologies that can be used in order to study either processing, communications, sensing. Essentially, one can see that it has to be a multidisciplinary effort, and it spans from solid-state systems, superconducting qubits, quantum dots, study of quantum fluids, nitrogen vacancy defects, atoms, different kinds, cavity QED, quantum optics, atomic physics, quantum machine learning. We are convinced that we have also a strong computing community in Brazil that we have to involve in this effort. Okay, after we talked to FAPESP governance, we set ourselves a few tasks. One of them was to put up this meeting. Another one was to try and look into the different quantum initiatives that exist worldwide. And so far, we've looked into 6 of them. It's kind of a coincidence because we are 6 people who are actually working on this right now. Some of them are, of course, leaders in the world, but others are also closer to our reality. And so we think, you know, there are lessons to be learned from all of them. Most likely, the first big quantum initiative to be launched was the European one, the EU flagship initiative. And it starts from national quantum technology programs or centers. The European community invested 500 million euros over 2 decades in future emerging technologies, European Research Council individual grants, Marie Sklodowska-Curie actions. They developed a European quantum technologies roadmap in 2016 with short, mid, and long-term goals. There's a reader-friendly paper in the New Journal of Physics from 2018, and there's a quantum manifesto from 2018 with over 3,500 endorses in academia and industry. In a nutshell, the quantum flagship involves 1 billion euro over 10 years, over 5,000 researchers in Europe and associated countries, and they have, of course, high targets. They want Europe essentially to be a leader in the future global industrial landscape in quantum research and technology. They have a strategic research agenda. They've all governance possibilities adapted from other previous flagships in graphene and the Human Brain Project. And there have been some calls already, and I think it's interesting to show what these calls have looked like. So this is from a recent call, and they separate in basic science, quantum communication, quantum computing, quantum simulation, sensing and metrology, and coordinating and support action. If you look at the success rate, so there were far more proposals in basic science, only 7 were approved, were funded. The rate is much better in the others. Of course, none of them have 100% success rate, but this is to show that they are focused on actually developing quantum technologies from this basic quantum science. Now, I'm going to go very quickly over communications, random number generations, computing, ion traps, superconducting qubits, simulation, neutral atoms, ions to computers, ultra-cold atoms, sensing, NV centers, atomic clocks, and also basic sciences. There are individual efforts in different countries. We looked into the effort in the Netherlands. If we look at the size of the community in the Netherlands, the number of researchers working there, it's not much different from the state of São Paulo. They have a very, very well-structured proposal. They estimate an annual cost of 102 million, of which the government would commit to 92.5 million per year. Now, Fred can correct me if I say something, if I miss something, but they are essentially integrating, right? They want to pioneer and set trends, develop applications, foster their international elite research, focus on earnings and training and retaining talent. They have a forecast, a timeline, which goes up to 2035, in which they believe one would already have a universal quantum computer. And so they are investing in all of these fronts: quantum computing, quantum simulation, communications, and quantum sensing, and they have different goals and different timelines for each of them. Again, they look at this in layers, beginning from research and innovation, expanding to an ecosystem, creating markets, infrastructure, human capital, and a social dialogue, which is something we will find in many of these initiatives. In Germany, they also have a very detailed plan. I cannot go into all of the details. I think it's interesting to look at the total number they have. Only in Germany, they are investing up to 2.65 billion euros. And one of the interesting aspects is they believe that this has to be closely related to informing the population, to involving the population in quantum science. And so they want to have endeavors involving museums, students, competitions in a very large country scale educational effort. They have, again, focuses in Germany, but also quantum computers, quantum communication, quantum-based measurement technology, so quantum sensing, enabling technologies for quantum systems. So all the ecosystem that goes with developing these things. They have also separate proposals which involve even quantum science in space, and also call for attention to proposals for what they call the Quantum Future, a program to support young top scientists in applied topics, something that we already have the means to do here in São Paulo with the young investigator programs from FAPESP. In the United States, there's the National Quantum Initiative Act that was signed to law on December 21, 2018. They have these interesting symbols. Actually, if you can look into the logo, it's an eagle in a cat. Again, non-defense, artificial intelligence and quantum information science are set here. They use the national agencies for this investment. So they're investing 400 billion in, this is over 5 years at NIST. I think this has to be wrong. This has to be in million. 5 centers for NSF, 5 centers for the DOE. The initiative, so I'm not going into the details of the initiative, but so I'm sorry, I know this picture may be offensive to some of you, so let me take care of that. The initiative is very detailed, and it looks a lot like a moonshot. So they have very specific plans and a lot of different avenues to be pursued, involving government, academia, public and private universities, industry, and of course, in the US, the military. Just to give an example of the private sector, of course, there's the huge companies, Google, IBM, Intel, Microsoft, Amazon, who are heavily investing in this. And there are all sorts of startups to develop quantum sensors. This, Felipe told me, is a gravimeter. He can give you more details later. We looked into Australia's quantum initiative, and it's very interesting if we look at the size of the country, if we look at the way the community is in Australia. It's extremely interesting, very detailed as well. I think it's very interesting to point out that they have expectations for the market revenue that they expect from quantum technologies up to 2040. Over $4 billion in revenue and 16,000 new jobs. And they split this in computing, sensing and measurement, and communications. They have estimates of what the revenue should be and what kind of job creation they could expect. They have 4 axes to focus and coordinate Australia's quantum industry development, research and development in viable technologies, assessing and developing capabilities. This is something that we find is extremely important for the roadmap that we would like to plan ahead before launching the program. Collaboration, making sure that both at the local, national, and international level, there is strong collaboration from quantum industry, from academia, and readiness. And this is probably one of the most important things that we would like to stress. This is coming. Quantum technologies will be developed. They will arrive. We should be prepared for that. We can either receive this technology and be on the buying end, or we can actually be active players in developing this. We have a strong academic community here, and we do have, especially in the state of São Paulo, we have a private sector that is capable of joining this effort and is interested in joining this effort. I'll talk a little bit more about that later. I was very intrigued to understand how they made the assessment. And so in their initiative document, they actually show the methodology for that. And so the methodology is basically to estimate what the market is today, to estimate a growth rate for this market over the years. So essentially, they look at the global opportunity for quantum technologies over the years, look at the share of these quantum technologies that Australia should capture, and then look at the potential for job creation by essentially looking at how many jobs per investment they have in each of these markets today. And so these are the numbers. Essentially, they believe that Australia should capture 5% of the international market in computing, sensing, and communications by 2040. I think we could be less optimistic about our possibilities in Brazil, but even if we capture 0.5%, we're already talking about reasonable economic revenue. Then there's India, and India was very bold in setting goals and announced a budget on February 1st. The budget is of 8,000 crore over a period of 5 years, which amounts to $1 billion. Okay, so this, of course, captured the news everywhere. India joins the quantum supremacy race, aims to build a 50-qubit quantum computer in 4 to 5 years. They have lots of strategic goals. I'm not going to go over all of them, but I'll give you a summary. And for the summary, they have a small community. They do not have a very strong quantum background. So scientifically, we are way ahead of India in terms of already having a well-structured, well-established community. On the other hand, of course, India has, for instance, a very solid space program, so we should not underestimate their capability of building on this and using these funds to develop a very strong and competitive quantum technology market. It's interesting to compare both the GDP and population. Their population is, of course, much bigger than ours. Their GDP is bigger than ours. But if we look at the GDP per capita, Brazil has a much higher GDP per capita. In looking over these initiatives, we actually looked at data from the UNESCO in terms of research and development expenditure and researchers per million inhabitants. So if you look, India is here. The research expenditure as a percentage of the GDP is not huge. It's below 1%. There are outliers like Korea, which is about between 4 and 5%. A lot of places that are between 3 and 4. And China, which is slightly above 2. This is Brazil. We can't read it, but Brazil is somewhere here. Maybe this is optimistic as of this year, about 1.5% expenditure. But if we look at the number of researchers per million inhabitants, we are definitely above India. Of course, if we look at other countries that I mentioned, Australia, for instance, is here. Marcelo sent me this only yesterday, I think. Marcelo Terra. This company, Stardust Insights, analyzed 69 startups all over the world, chose 5 top emerging quantum computing startups, which are here. But I think it's interesting to look at this map. Of course, there's concentration of startups in Europe, in the US, on the East Coast, on the West Coast, some startups in separate places in the country where they have strong research. Interestingly, Brazil is on this map, okay, and this is encouraging. If we look at the local community, we have an academic community in São Paulo, which is already strong and young. We made preliminary searches on Biblioteca Virtual, the virtual library of FAPESP. This is the support in numbers with these strings searched, so quantum information or informação quântica, qubit, ótica quântica, or optomecânica. Over 367 research grants and scholarships. I think this is very revealing. A large number of young researcher awards. So we have been able to attract young and talented people to the state of São Paulo. we need to build on that strength. This is an evolution of the grants awarded by year. We can see that we have some effort up to the year 2000. From the year 2000 onwards, with the Millennium Institutes, National Institutes for Science and Technology, the subject became a lot more appealing, and one can see very clearly a trend for large growth. We've already established a very strong scientific footprint with publications in very prestigious, high visibility journals. I'm not going to go over all this. A lot of you in the community know it. It's just to showcase that, again, we're building from a very strong scientific academic foundation, right? This scientific footprint, if we search for specific terms in a database, Scopus, we can see that the number of citations has been growing. There are some hiccups, but it's essentially steadily growing, showing that the community is making its mark internationally. And again, high impact journals, almost 100 papers published in PhysRev letters from this community alone over these a little over 10 years. So what's the structure that we envision for this initiative? Not only what is the structure, but what we believe is the role that FAPESP should play. We need to build a roadmap that has to encompass, of course, an academic throughput. This is the part that is already, very strong. We need to develop a startup ecosystem to make it, create an environment that is stimulating for developing these technologies. We need better communication with industry. In the preliminary talks that we had with several partners that you will see, the response was extremely encouraging, right? And of course, we need a strong connection with society, both at the educational level, better education about what quantum means. We need to get rid of quantum nonsense, but also involve society in the effort. We've talked with a number of people internationally. This is a selection of people whom we've talked to and whom we would like to have help from to establish an advisory board, an international advisory board, and evaluation board. Now, as I need to stress that this is only preliminary. We've talked to these people. All of them were very, very encouraging. But of course, we intend to have an advisory board that will be diverse geographically and in terms of gender as well, in order to foster true collaboration and stimulate everybody to take part in this initiative. These are private sector endorsers. We had conversations with IBM, Petrobras, Microsoft, Thor Labs. We had very, very productive conversations with Werner von Braun, who are very excited, and I am sure will be very, very close partners in the whole initiative. And of course, Embrapa Agrorobotica, because we believe that there are strong possibilities for agriculture from quantum sensing. I've already talked a lot. I just noticed the time. I think I should probably stop here, but give you two perspectives. One of the role that we believe FAPESP should play in all this. Why do we want to establish a program? Is it because we need more support for quantum information science in the state of São Paulo? Not really. We believe that we are strong and that we have all the possibilities to compete for funding from FAPESP with no problem. We believe that FAPESP can have a very important role in inducing initiatives in focusing both the academic and private sector communities to not lose sight of the possibilities, to take advantage of the possibilities that we have to build on the academic strength that we have, and also the private sector, the possibilities for the private sector. We don't have many startups, we don't have many companies investing in quantum technologies at present, but we think that there are lots of encouraging endeavors that have been undertaken in the past. In particular, I mentioned it's time for some serious quantum optics and quantum information, building the first synchrotron, and serious involved a lot of work by companies in Brazil, developing novel technologies that are state-of-the-art worldwide. And so I'm very pleased that Harry Westphal Jr. is attending today, because he has an address notebook that we are very, very interested in sharing in order to attract these companies and explore possibilities for the development of quantum technologies. Program from FAPESP means essentially coordinating these efforts. We've talked to Carlos Joly, who started the first of these programs, the BIOTA program, and he told us when they started this, when they proposed the program, almost at the same time, they presented, I think it was 10 proposals for thematic projects. Of course, proposals for thematic projects will be very welcome. We would like to have a significant number of proposals for the entrepreneurial programs of FAPESP, PIP and PICH, technological effort. We do not want this to be something where we say, yeah, there's a lot of promise from quantum information science, but the practical near and midterm technologies are sketchy. No, the effort that we have ahead of us for the next many months is to really build a roadmap where we can pinpoint certain technologies that have a very, very high probability of being successful in the near and midterms. So with that, these are the milestones that we're looking into, building this roadmap, looking at short and midterm technologies, leveraging impact in industry. Of course, we will need a highly skilled workforce, so that's where academia comes in strong. We have a strong background. We have to build on our strengths. We have to strengthen our weak points, spread the community across institutions in the state. We already have people in many different institutions. All the major universities in the state have people working in this field. And in terms of visibility, not only increase the public awareness, but also the public education in quantum science in general. And so I think I'll stop here and thank you for your attention. I'm sure I didn't cover everything that we studied over the past few months, but we have the brainstorming session in the afternoon, and we can complement on that. Thank you. Gustavo, would you like to moderate questions or comments?
Yes, sure. Okay, so I think it's 10:53. We are a bit ahead of our planned schedule. So I guess we got a few questions from YouTube, and in the chat here, there aren't many questions so far.
But
So
Marcelo
if someone wants to
raised
start,
his hand.
we can make a short discussion here. But remember, guys and girls, that there will be time after the morning session. We could extend a bit on questions in general, but also in the afternoon, there will be a full-on brainstorming that we can deeply discuss whatever doubts and suggestions you might have. But of course, we can take Marcelo's questions. Marcelo, please.
So actually, I have more of a comment than a question, which is, well, actually, first of all, thank you, Paulo, for the presentation. It was very broad and interesting, and really gave a very nice picture of the whole thing. And I'm glad that we are recording it, because I'm gonna use it from now on. The comment is in the direction of if I'm not wrong, and Arthur is much more qualified to talk about it than me. I saw that he was in the panel that you guys consulted. But Singapore's approach to development in the 60s and 70s, when they became independent, was a smart approach, which was to focus on one particular point, one particular product, for example, develop very quickly the industry towards that product and become one of the leaders of the world in that particular product, and then understand that when they saturated on that and switch quickly to a new product or to a new concept. And they played it like this for a long time, and they built up a very solid economy by doing this. So in that sense, my comment would be in the direction that maybe this could be a good strategy for us as well. Instead of trying to develop all the concepts of involving quantum computation, try to find out which is the one that we have the best chance of really getting a larger share of the market, focus on it, but also doing it, also preparing to switch as fast as we can as soon as we realize that we've saturated. So this could be, so for example, you've mentioned, and I think that this is a very promising strategy for Brazil, you mentioned sensing. I think that sensing is one of the areas that Brazil has lots of quality in different technologies, different physical setups, different. So we can approach sensing from nonlinear optics, quantum optics, condensed matter, and so on and so forth. And we already have lots of labs working on sensing one way or another, maybe for fundamental physics, some of them already targeting the industry. So this could be one good strategy. So to choose one subject, maybe sensing, maybe some other, I don't know, but to really build very quickly, as fast as you can, as strong as you can, and go for the share of that market there, and also prepare to switch as soon as possible. So that was my comment.
Thank you. I'm not sure I'm going to respond to all comments because, again, we have the brainstorming session in the afternoon. I would just like to comment that is our view as well, that sensing is the most promising aspect for which we can develop near-term, mid-term technologies. So we have that in mind. But we have some other things in which we think in the near term we can develop technologies. So I would say, Marcelo, at this point, we really want, and also this is one of the main reasons for this meeting, we want and we need input from the academic community. We would like the academic community to be strongly involved in really coming up with ideas that can reach market in near or midterm. Okay. Ideally, we would like to submit the proposal for a program to FAPESP even before the program is started, with a few axes very specific already in mind. And as I said, ideally we would have already simultaneously proposals for funding in joint efforts, academia, industry, or just industry, right? Seed money from FAPESP to begin the development of these technologies. I don't know if anybody else would like to make a comment. I really would like to, everybody to know that this has been a 12-hand, 6-head effort so far, and that of course all the others are, could reply as well as I. So Celso, you have this question from YouTube. Maybe you would like to comment on this.
Hi, can you hear me?
Yes.
Yes. I guess the point is, how can we use machine learning to create quantum algorithms? I'd like to comment a little bit more, but I have no experience specifically with machine learning. But I guess it's a promising area. So people has been using a lot of machine learning to many applied sciences. So I guess it's a good point, but I have no idea. I'm sorry.
Okay, I think we could postpone the brainstorm. Maybe there's some experts on machine learning. You can bring them in the brainstorming session. And I would like to thank Paulo for his presentation and Marcelo for his questions and comments on the outcomes of this initiative. And I would like to invite Marcelo Martinelli actually to introduce us the next speaker on queue. Please, Marcelo, take the stage.
Okay, thank you, Gustavo. It's my pleasure to introduce you to the first presentation of the day. Professor Nicolas Treps is currently at Sorbonne Université. That comes from the merging of the old Sorbonne and Pierre-Marie Curie, and is now is the co-founder of the Cailabs, a startup on the fields of quantum optics and optical applications. It's my pleasure because we've been working together way back in the early 2000s at Laboratoire Kastler-Brossel in the same setup. So it's quite nostalgic to find him here in Brazil, although virtually. And we've been collaborating or keeping in touch for the last year. So I'll leave you with Professor Nicolas Treps.
Marcelo.
Hello.
Would you like to show us the picture that you uncovered? I made you co-host. If you,
okay,
yeah, if you.
So, okay, it could be. I'm wondering if I'm co-host. Oh yeah, I can share it. So, I hope that Nicolas remembered that picture. Can you see that? Or
okay. Yes, I do.
Okay. It was quite a time ago.
It is definitely.
And the lab has completely changed completely. Not to mention, not to mention the hair of some of the participants on the picture.
Yes, indeed.
That said, Nicolas, you're welcome to introduce us to the experience of running a company now. That sounds fantastic. So please, the floor is yours.
Okay. So I cannot. Sorry, because I got disconnected just when you started your presentations. My Wi-Fi went down and it's back. So I'm not co-animator anymore. So I cannot share my screen. Could you put it back to me, or someone give me? Here it is. Good.
Okay.
Voilà.
Merci.
Merci beaucoup.
I guess I can do it in French. Okay. Well, good morning, yeah, for you, everybody. I think you can see my screen now. It's fine. Yeah. Okay. So good morning, and thanks a lot for the invitation. Indeed, it's really a pity that I am not with you in Brazil, but I guess this is for next time. But at least it's nice to set up this kind of meetings, and I could follow a bit the presentation from Paulo, and I do agree from all his points. And it was interesting to say that to see that you mentioned that what really you are looking at is about sensing. So this presentation will be somehow a bit about sensing. Well, it's not a typical quantum technology company, because the company you will see is not quantum, but it comes from quantum metrology, and it goes back in the labs, in fact, for the same purpose. And this is this kind of story I'd like to show you today. I want to stress also, you can see below that, sorry, I need to, this is fine. Okay. You can see below that in France too, we are trying to structure all what we do. And so we have now in my university a quantum information center. We are developing some new quantum hubs and so on. And I'll be happy to share this information with you at some point. Okay, so let me start. We start very basic so that we are sure that we all speak about the same thing. And then I will move on. I'll explain you a little bit the science, which is behind the company, some of the things the company do, in particular, how it was developed, and then finally, how it went back to the lab. But to start with something very simple about sensing with photons, which if you make a measurement with photons, which is an actual measurement, you see that you have 5 photons coming in a quarter of a second in this experiment. And then if you do statistics of that, so you do many of these kind of measurements, and you plot a histograms, what you know is that you never measure the same number of photons. So here, the mean value of photons you would measure is around 3 or 4, but it's never the same. And we all know about that, and this is called shot noise. And this is what is usually known to limit the sensitivity in measurement with light, the standard quantum limit for absorption somehow, and it's given by 1/√n, because of the Poisson law of photons. But as you know, light is not only about photons, it's also about electric field. And I want to start, and before really starting my talk, to give a second talks about how we describe quantum electric field, to be sure everybody agree with that. So if you look at maybe the only, a few questions, but not many. If you look at the electric field operator in a plane wave basis, you know that the difference between classical and quantum descriptions is that we put annihilation operator here that goes to the fact that each mode is a quantum harmonic oscillator. And so in each mode, you have energy levels that you can see on the left that corresponds to the quantum harmonic oscillator. And you can make the parallel between position and momentum of a particle with amplitude and phase of the electric field. So this is what people usually do, and this amplitude and phase, in fact, it's better to call them the real part and the imaginary part of the field, and which are named the field quadratures. What I want to stress here is that when you have a classical field, it can be represented in the Fresnel diagram in this very simple way. But because we have a quantum field, we have noise coming from the fundamental state of our quantum harmonic oscillator, and which makes what we look in the vacuum. Vacuum has electric field fluctuations. And then when we combine both the classical and the quantum approach, a very naive idea is to say that an actual field, so an actual laser beam, is a classical field plus the vacuum fluctuations. And it is these vacuum fluctuations that do limit the sensitivity of your measurements, in particular for phase measurements when you're not counting photons. Okay, so these are the two sides of the quantum limits for estimations with light. So with that, I will go now a bit deeper in the theory of that, but very light things, to explain what we do in our group, and then move on with how it can lead to a company. So if you want to formalize a bit more parameter estimation with light, so this is a very generic slide about quantum sensing with a beam of light. So what happens usually? Well, you want to probe an optical system that depends on the parameter P that you wish to measure. To make it simple, this parameter P can be a distance between two points, a position of a mirror, dispersions, or whatever effect that can be probed by light. After the light has gone through your optical system, it depends on the parameter P. Then you perform a measurement, which gives you classical data. You do post-processing of your data to try to estimate the value of this parameter. So E of P, as written here, is called the estimator of P, while P is a parameter you want to get. So this is a very well-known problem, and the sensitivity can be calculated, the ultimate sensitivity, and it's called the Kramer-Hall bound, which is what is the information you can extract, whatever the estimator you calculate, and whatever the possible measurements you take, and in particular, if you take the quantum version of it, whatever the POVM, so whatever the quantum strategy of measurements you act on your end. You can have a very simple formula for how this works. Very simple because I'm not expressing the details of the parameter, but the uncertainty or the noise you have in the measurement of your of P is always bigger, so sensitivity is always bigger than 1 over the square root of Q, which is the number of measurements, and F, which is the Fisher information. And all what we have to do as physicists is to calculate the Fisher information. So I don't give it here, I will give it in a simple example later. So this is a well-known problem which has been studied for a long time, and I think one of the first papers which really formalize that in a proper way is this Hedstrom paper that shows how you can optimize quantum states and measurements to reach the ultimate limit. So what that it derives, it shows that if you want to perform the phase measurements and you have n photons, so which is the total energy, the best estimator you can get is as a sensitivity which scales as 1 over n, and this is sometimes referred as the Heisenberg limit. And there are schemes to reach this Heisenberg limit. They are not simple schemes because the quantum state you need is a so-called null state. So you need a superposition of an n-Fock state with the vacuum and put them in an interferometer, and on top of it, perform a quite complicated photon number resolving detection. But this gives you the ultimate limit. However, when we perform measurements with standard light, the advantage we have is the mean photon number is much bigger. So this gives you the ultimate limit here, but it's not practical when you want to go to large photon number, because there's no way we can generate this kind of thing. So in the large photon number, usually you restrict yourself to Gaussian noise or Gaussian states, because they do correspond to what you get in the lab. And here, for example, what the Cailabs did calculate, we can demonstrate that if you are in the presence of shot noise, the main sensitivity, the best sensitivity you can get for phase estimation is given by something like 1 over square root of n, and sigma n, I will come back to that later, is a parameter that can be tuned, and which is called squeezing. So we have a very different scaling here, but the advantage that for a laser beam, sigma n is equal to 1, and you have, if n is large, you still can get a very large sensitivity. Well, how do we perform these measurements? I did hesitate. So this is the same as before. I wanted to show that what happens when you do perform a measurement with light. So how do you measure this phase? Well, you don't measure phase directly. You do interference with a local beam. So you do, this is still in French. It is the French detection en mode, but I guess you get the point. So you perform this, and on the right, which is more interesting, these are actual measurements you get when you measure, make interference to measure your phase through chromodine detection. And this is what I mean by Gaussian states. It means that the statistics of your measurements is Gaussian. So this is what you have on the right in the history. But what physicists can do for now a while is, so this is the Gaussian representation, is to develop squeeze states. So what we do in the labs is that we change this probability distribution, this quasi-probability distribution which is below, which is Gaussian in both quadrature measurement, to a squeeze state in order to improve your measurements. There is one thing I wanted to mention here, which is not directly related to what we speak about today, but it's related about quantum technologies and how we do quantum technologies with continuous variables, because this whole domain, when you measure quadrature, is called continuous variables. In this example I took here, when you have coherent states from laser beams, or when you have squeeze states, all the statistics you measure are Gaussian. So they can be changed compared to the vacuum. And if you look at this one, if I manage to do that experimentally, in one direction, I have less noise than the vacuum noise, and I can improve my measurements. But it is still Gaussian. So what I want to insist here is that this kind of quantum states, they are very useful for quantum sensing, and this is perfect, this is what I will speak about today. they are not enough for quantum computing, because when you have Gaussian statistics, you can demonstrate that it can always be efficiently simulated with a classical computer. And what we work on in our lab, and we are not the only one, is to talk to these squeeze states and try to change the statistics to make them compatible with a quantum computing approach. Okay, so now let's combine this kind of description to the phase measurements I've shown you before. Another point which is interesting in this diagram, so this I'm back to my phase measurements, is that when you do the calculation, in fact, of what you measure here, when you calculate this difference, even classically, the difference comes from the E2 field, so the field that comes from the empty part. When you make a measurement with our, again, experimental data, you see fluctuations, but the noise in these measurements come from the vacuum input inside your interferometer. So the ideas of a physicist, and again, I think Carl Cave was the first one to suggest that, is to remove this vacuum and change it from a squeeze state. So in a drawing like that, it's very easy to take a squeeze state. So this is a typical squeezer. So you have them in Brazil, you can show, and you put them inside your interferometer. And if you look at your measurements here, you see that the gray points have a smaller dispersions. So you have an increased sensitivity in your measurements when you use a squeeze state. Well, I guess many of you know what is the first application for these squeeze states, and I had to say, you know that now these squeeze states are used on a daily basis in the large-scale gravitational wave interferometers, which are Michelson interferometers, and they do exactly that. They put squeeze light in the empty port of the Michelson interferometer, and they increase the sensitivity, as you can see here. This is an example for the LIGO collaboration, but now also the European one, the Virgo collaboration, also has a squeeze light inside the interferometer. And they gain in practice a factor of 2, thanks to squeezing light, so factor of 2 compared to the best you can do in the presence of vacuum fluctuations. So this is a big thing. It's recent, but it's a very big thing for the field, which means that squeezing really can be used in practical applications. I want to move on a little bit now and to go to a specialty that I guess Marcelo does well, we've been doing that together for a while, is to increase the number of nodes. So go to multi-mode approach to Gaussian statistics and to go to a bit more complex measurements. And this is where we made an innovation at some point. So for that, this is the exact same slide as at the beginning of my talks, but now I consider that the noise I have with my light beam is only Gaussian noise. And this is nice because when I have Gaussian noise, I know how to do calculations. They are easy in that case. So then I can calculate, in that case, the exact practical limit for parameter estimation in the presence of Gaussian noise. So here I made that calculation. So you see that the best estimator you can get has a variance which has to be bigger than this formula when you have the new terms, which is PC. And PC is a normalization factor. So this is what gives you the unit of your measurement. And it comes from the normalization of this derivative. And in fact, it tells you how fast your field varies as a function of the parameter. Okay, and this is normal. If your field doesn't depend on the parameter, you have no sensitivity. If your field depends a lot on your parameter, you have a large sensitivity. And then you keep here the sigma n, which is your squeezing factor, and below the number of measurements and the number of atoms per measurement. Well, let's apply that to an old problem now, but I need to present that if I want to present the idea of the company. So this is something we did in the early 2000s. We wonder how can all these concepts be applied to simply measuring the position of a laser beam. So now you have a laser beam which is moving, and I want to position it as good as I can. And here, I really want to move a little bit into how we approach this problem, which is at the heart of the creation of a company. So we realize something which might sound very simple, that well, you can do all the complicated Kramer-Hauer-Bond calculations, but when you have small displacement, a very simple undergraduate calculations tells you that if you take your electric field, which is displaced by a displacement d, which is here, you can do a first order decomposition and say that this is your electric field. So E of x is your electric field here, plus d times the first derivative of your electric field. And if you translate that into beam shapes, your displaced electric field is a Gaussian, which is displaced. This is the one without displacement. And after, you have the derivative of this beam, but you know that the derivative of a Gaussian mode is a Hermite-Gauss 0-1 mode. So what you have here is a first order Hermite-Gauss mode, which is multiplied by your displacement, so which contains the information for your displacement. And here you can calculate your Kramer-Hauer bond, and the W0 is this one, and in this case, W0 is simply the waist of your laser beam, so the size of your beam, times this parameter. So how knowing that, we can do an optimized measurement of position. Well, we do homodynamic detections, so that's quite simple. We have our beam, which is moving, so when it moves, it contains some of the 0-1 beam, and we interfere it with a strong Hermite-Gauss 1 beam. So that interferences happens only between the 0-1 component of the beam you move and your strong beam, and this one, so the original one, you don't see happen. And when you look at the difference, you get exactly your displacement. So this is just an interferometric measurement to extract one mode you need, and it's fully classical. But the noise in the measurements is, as in the interferometer before, is given by the empty port in your measurement. And in that case, the empty port is the 0-1 mode before the displacement. Because before the displacement, you have a strong 0-0 beam plus vacuum in the 0-1. So this is the noise in your measurement. So with this, and you can get, even with the standard laser beam, very, very good sensitivity, so down to the angstrom level. But what is interesting for what we are speaking about today is that if I change the noise in my 0-1 beam, and I change it from a vacuum to a squeezed beam, then I can improve the sensitivity of my measurement. So this is the actual result from the paper that we gained at that time, I'm not completely sure, but a small factor of 2 in the sensitivity of position. Well, there is a big if in what I just said, is that the if is if I change the vacuum mode to a squeeze mode. So how do I do this? And this is all the interest of this kind of field, is that you have to develop classical technologies to mix different beams. So we have to mix a current beam with a weak squeeze vacuum in a different modes to engineer this light. And so in order to do that, we developed a new apparatus, which is at the heart of our innovations. So just to say, we called, and this is my colleague Hans Backer, at that time it was a collaboration with Australia, that's why I put that. So my colleague coined the name a quantum laser pointer, which is always useful to have a good name. And we could do a multi-parameter positioning with this kind of techniques. Okay, so I think it's time now. You have the background of what we have been doing. And the point is, how do we move from that to a company which is in fact purely classical? Well, this took quite a while, and the story I will tell you is nearly chronological, but not all. And in particular, this slide, we didn't know at the time. But this is something we learned actually a few years later. Well, this part we know. So we knew that internet traffic goes through optical fibers, that you know, and transatlantic one, all over the world. And that one of the problems is the saturation of these channels. What we are not fully aware is that the saturation was really completely fundamental, meaning that people have used all the possible degree of freedom of light to increase data transmission within a single mode fiber. So encoding in a fiber is done through power and phase, and the channels are polarization channels and wavelength channels. But once you saturate your Shannon criteria, well, you cannot put more information. So you have a problem. And what people from telecom are suggesting, and were suggesting at that time, is that maybe we should move to encode informations in our optical fibers using spatial modes. So to use imaging, to use a spatial degree of freedom of light in order to encode. But what is the difficulty here? Well, there's one which is making the fiber, but this is not our work. Big companies are doing that. The other is to put into your fiber all these modes. So to mix them and to put them into the fiber. And if you see, this problem is very similar to the one we had before. You have to combine different modes with different shape without losing your information. And this is what we know how to do. So in practice, it looks like this, like this, sorry, but we know how to do. What we know how to do is to take different beams, which are Gaussian beams, so different laser beam or different single mode optical fiber, and combine them together so that each fiber, each single laser goes to a single beam, but to a different spatial mode. And if you do that well, this is a purely unitary transformation. It means that it can be exactly undone without any loss of information. So this is really a way to encode, would it be quantum or classical information. And from these two facts, we decided to start a company whose name is now Cailabs, and I will try to explain you a little bit how it does and how it was developed. So I just told you what it does. It takes single mode fibers, put them into one, and encode them into different modes. If you want a bit better diagram, this is what it should look like. So what we want to do in this company is to take independent optical fiber, like here, put them together in a Cailabs system, then light travels in a multimode fiber, and at the output, we have the exact same apparatus, but put it the other way. And so you have a multiplexing, demultiplexing of information. And of course, if you want to keep your data rate, this has to be compatible with the other encoding. So this is on top of wavelength encoding and polarization encoding. I guess what is interesting for you is how this kind of project emerge and goes to an actual company. So I decided to put on the timeline. The first demonstrations of our system is 2009. We call it a universal programmable light converter at that time. And we made the implementation for quantum optics. At that time, I had a PhD students in collaboration between the group in Australia, so Hans Backer and our group. And my student was very motivated with valorization, which was a good thing. And thanks to him, we decided to put a patent, even if at that time we didn't identify an exact applications to the system that allows to do the mode mixing. But then we met during a conference in 2011. We met people from Alcatel-Lucent, which is Nokia now, and they told us the fact I've shown you, that they are looking for increasing the data rate in optical fiber using mode multiplexing, and they don't know how to do spatial mode multiplexing. So we joined Alcatel for 1 year, and we had a small seat in a large European project that gave us a little money to develop a proof of concept in 2013. In 2013, which is where all happened now. So this is 2013. In 2013, so we both did the proof of concepts, which was able to mix 3 modes in both ways, so mixing and demultiplexing, and looked at the performances, and decided to create the company Cailabs. Soon after, we raised money. So in fact, we created the company in order to look for money. So the company was not really, was just existing on paper and was not doing much apart from trying to find money. And we found money from an investment fund called Innovacom. It took quite a while to get a patent licensing. And this is usually an issue for academics, is to interactions between companies and universities is not always easy on that level. But anyway, what is important here is that in November 6, we signed our investment, which is about a bit less than 2 million euros, and really started the company. And in January 2013, we had the first sale of the company. I like to show the team at the beginning. So this is a photo which dates from, I think, January 2014. So it's 6 people plus me doing this company. And when you start a company, and I tend to say sometimes that my main contribution to the company is in fact to find the good people to work there. Because now the company is living its life without me. So if you want to know, so Jean-François is now the CEO of the company, and he did his PhD with me at that time. And most of them, in fact, did quantum optics, so, which is, you see, it opens perspective to do quantum optics. I encourage you to do so. And then this is the first system we saw that I can tell you. You see, this is a big box. So this is the 2 orange box, are multiplexing and demultiplexing, which is not compatible with industry, but that's fine. This was a prototype. Okay, so let me move on now to a small part about what is Cailabs today. So the company is settled in Rennes, so maybe with a little map it helps. So Rennes is west of France, in the heart of Brittany. So this was our first location. So since then we moved. We have about 1,000 square meters. And the company is 7 years old now, and now it's quite big. So it has more than 50 employees, about 20 PhD students and 20 PhDs. And all in all, we raised about 16 million euros all along the career of Cailabs, and have a lot of patent families. I'm running a bit late, but I still think it's interesting to show you this short movie. I managed to get my pointer. Sorry. Here it is. So this movie, we don't need the music, tell you a little bit how it works. So in fact, what we do is that we use phase plates. And when a beam goes through phase plate, it gets deformed. And this is nice because it's unitary. And when you put many phase plates, you have a phase deformation. And what I told you at the beginning, when your beam is moving, the information about the displacement of the movement of your beam is encoded into the higher order Hermite-Gauss mode. And this is exactly what we are doing here. And by looking at that, we can, if everything goes well, in fact, measure turbulences, but what it is at the end of the day is measure the displacement of your beam. From that, people are a lot of thought, and very recently, there was this kind of paper which is very close to what we did a long time ago, but with a subtle difference. So now what you want to do is not position a single beam, but now you want to see the distance between 2 incurrent beams. And the model problem for that is that imagine you have stars in the sky, and you have a little dot, and you want to know if within that dot you have 1 star or 2 stars. To which sensitivity can you do that? This also has application for biological samples. When you have fluorophores, you want to know if you have 1 sample or 2 samples, and to which sensitivity. What people have calculated, in fact, is very similar to what we have done a long time ago. But if you have incurrent light, here again, information is encoded into Hermite-Gauss modes. But before it was encoded into the electric field, so the amplitude of the field, now it's encoded into the intensity, because you have incurrent light, so the total intensity is the sum of the 2 intensities. Well, if we measure the power into, maybe I make it whole, if we manage to measure the power into these different modes, we can get a sensitivity, which is written below, in the measurement of the separation between these 2 incurrent beams with a quantum limited sensitivity, which is the best we can do. So this is what we have done in our lab. We took this system, so we took 2, not 2 stars, we took 2 incurrent laser beams, and this is a lab experiment. We use our demultiplexer, split all the Armigos modes, and by measuring the output of all the Armigos modes, we could show that we could get a sensitivity in this beam separation, which is much improved compared to the Rayleigh criteria, and which reaches close enough the Kramer-Hauer bound. In practice, it does not yet reach the Kramer-Hauer bound, and there's a lot of interesting theory to do behind because of imperfections of the system, because of crosstalks. But what is interesting here is that we don't have only 2 outputs, we have 9. So we can do multi-parameter estimations and go really on the quantum sensing regime. Now it's with classical light, but we can do it also because it's unitary with quantum. With this, I will conclude just a picture from our group. And I just want to insist on the 4 permanent people we have in the group. You can see now on the left, one that many of you know very well, which is Claude Fabre, really at the origin of many of this multimode approach to quantum light, which is our emeritus professor, but still comes to the lab. And Valentina and Mattia, Valentina doing experiments along with me, and Mattia being a theoretician. We work all together in art. And with that, I thank you for your attention.
Well, we thank you, Nicolas, for this very exciting talk. I guess there will be many questions. I would like to invite everyone to raise their hands so we can direct the questions. You can direct yourself the question to Nicolas. Just remember to open your mic and your video if possible. And I'm sure Nicolas will be happy to take them. Okay, maybe before people start putting their questions, I can start with one. I was very impressed, Nicolas, by the speed actually that you get out of the lab demonstrations and jumped into the partnership with Alcatel in 2012-13, right? So is this a collaboration you guys had already with Alcatel, like a sort of a flow of information, or this was a first start interaction?
No, it's a bit of both, but it's mainly a bit of luck here. So Alcatel Labs is not far from Paris, and they do optics, so we know a little bit each other. But really, this is a coincidence that we met them during a conference, and they saw a presentation from Jean-François during that conference. And then they came to us to tell us this is it. So it's part of luck. So I don't know what would have happened if they didn't see that presentation. If one day would have created the company, it's hard to know. So yeah, it's part of it. But on the other hand, it tells you that it's important to communicate your results, whatever conference there is. It's a useful thing.
Okay, thanks. Let me see here this. Not seeing any raised hands so far. Does anyone?
Marcello has one and is raising his hand directly.
As a co-host, I cannot raise my hands.
Oh, you're right. Yeah, please go ahead, Marcelo.
So, my curiosity about the approach to Alcatel is how it began. It just fortuitous, or Alcatel? Somebody from Alcatel heard of your work. What was the dynamics?
You mean with Alcatel?
Yeah. So who got in touch with whom first?
So it's through the conference. Alcatel come to speak to us really at the end of the conference.
Mm-hmm.
And then they had a quick chat with Jean-François, and they decided we organize a meeting, and we organized a meeting all together, maybe a few weeks later. And then at that time, it's interesting because you have to make a decision. Do you build a scientific collaboration with them? Or do you be a bit careful because you know, okay, maybe I want to make a company and I don't want Alcatel to make the company. And this, again, is because Jean-François was really motivated in making a startup company. And also Alcatel was a bit, they saw the product, they thought it could be interesting, but they didn't want to invest their own force within that. So in fact, when we decided to join Alcatel on a European project to make a demonstrator, to the point, Alcatel already knew, and we told them that if the demonstrator worked, we would create a company and we would sell them the system. But they agreed with that. I mean, for a big company, in fact, they don't want to develop this small thing within their world. It's too complicated. So they were happy to support somehow indirectly the development of a small company that can be useful for their own market. For me, that's the way I see it.
So you know how Alcatel use that usual dynamics of them, of approaching groups and backing them up to start their own companies, and or it was the specific case of Cailabs. So often they do that. They go after companies, and instead of buying the patent or trying to develop the product themselves, they'll be backing up small groups that would start their own companies and become sort of, and then Alcatel became the customer of those companies. That would be the usual strategy.
Yeah. So it's hard for me to answer that. I'm not completely sure. It's a model of some companies. So Alcatel now has been bought by Nokia, and it's not really. So I don't know what is their policy now. So I don't really know. I want to stress that I think in France, and maybe the same in Brazil, the problem we have is actually companies don't look enough in what academics are doing. And the reverse is true. So we lack communications. But then once the startups do exist, from what I can see, usually the relation between startups and big companies are fine. And indeed, if the companies, they always have in mind that if the startups works well and interesting for them, they will buy them. So this is not our model in our case, because Alcatel is not really much into the player anymore, but yeah, that's about that.
Okay. Thank you.
So we have a...
Citelinto raised his hand.
Yes.
Yep. Please, Daniel, go ahead.
Yeah.
Hello. Hi, Nicolas.
Hey.
But no, I wonder if you can discuss some, maybe there is some parallel development for quantum applications of this technology, because it looks like it's the kind of technology that you can have different applications for quantum information and sensors. So can you comment a little bit how it developed also in the universe, this kind of ideas?
So, let me give you an answer and tell me if it's what you need. So, what is interesting here is that Cailabs company has a market which is about classical things. So, they are interested in improving the product, but not that much in trying to find quantum application. Yeah. So, in fact, me, I don't know, I forgot to say, but me now, I really very barely go to Cailabs. So, I'm just a scientific advisor. But Cailabs lives its life without me, and I'm full-time professor at university. But then this is what I do. So because I have access to the product, and I try to valorize that to quantum application, because as you said, I really believe it can facilitate a lot of quantum application using light. Because here what it does is as I said at some point, what we are doing is a multiplexing of information. Would it be classical or quantum? Because it has very low losses, it should work very well for quantum information. So there's many perspectives. I've shown one here, which is about quantum metrology. I have one colleague that tries to encode, to use it to do multimode quantum memories, for instance, so to shape light to encode inside multimode quantum memories. But there's many things that could be done. But this is what we do in universities. This is the company doesn't do it, but is happy to support from time to time by giving us products at a discount price if we need that and if we do it together.
So I mean, specifically, so you are able to use some of this because there is a lot of engineering behind this technology. Yes. So are you able to use this engineering back in the university develop more quantum technologies?
So we can buy the product itself. I cannot have access to the process to make the product, even if I know. In fact, I know how it's done. So, but what is important, in fact, is to have access, and this is something that can be shared. Is to have access what is possible to do, because indeed, what is remarkable for me, what I didn't expect at all, if you have a system which is completely passive, very small, interferometric, and stable for years, which I would not have expected is possible.
Yeah, that's really impressive.
All is glued inside. But in fact, you have the photos. You can see a bit. Show the photo here. The system is. This is not the last version, but it's one of the last version. And you see all these glass blocks which are glued together and just do not move.
Thank you.
And that's a good point. This kind of technique, it's good to know it can be done, because it tells us that in our experiment, maybe we should try to do the same.
Thank you.
Okay, thanks Daniel and Nicolas for the discussion. The next on the list is Thiago Alegre. Go ahead, Thiago.
Good morning. Hi, Nicolas. Thanks for the talk. So I actually want to know about how did you balance your research and your involvement with the company? So I think that's we are trying to build a quantum initiative here, but we want also to involve the private sector, and startups are a good starting point. But there's always the pressure from the research side that you have to have PhD students, to have publications, and the needs for the startups and for the companies are very different. So if you could share your personal view on how to balance that, or how did you did in the past, how did you balance these two worlds, and how did you come up with the idea?
Yeah, so this is indeed a very important issue. And as you said, I will give you what I did, but there's as many models as people, so people would do differently, and that's important. So the way I've done that in my side, so first, I would not have started a company if I didn't have a PhD. I mean, not me, so former PhD students or whoever, which want to carry on the project. So me, I didn't want to leave completely my job, and looking for investors and something is a full-time job. So it's my student, Jean-François, that decided to go full-time on that. But still, on my side, for the first year of the company, I help a lot in building the team, in, of course, developing the product, patenting, licensing, and so on. So while somehow, for 1 year, I mean, we all know that, but for 1 year, I had the impression to have two full-time jobs. And I should say that at the end of 2014, I needed a break. That was far too much. But it was fine, because anyway, after that, I was happy enough that the company was working by itself. It has a team of 10 people which were very competent, and they didn't really need me anymore. So after 1 year, I decided I would be back mainly in the lab and devote to the company 10 to 20% of my time. So it was, before it was 20%, and it's going down every year, let's say. So now it's more like 5-10%, I don't know. But now they are real 5-10%. Before they were supposed to be, the first year they were supposed to be still 20%, because this is what French law tells you. If you want to keep your job, you're allowed to devote 20% of your time to the company, which was not true at all. It was a large part of my time. But this you can do, but you have to decide. For 1 year, somehow you have no choice, because you don't know what will happen. But after, you have to make a choice. Do you want to leave your academic job, or go back and find good people that will take care of the company? So this was at least my point of view.
Can I just ask another question, Gustavo? Yes. So I already started. And can you also disclose about your funding for the company? So if it was mainly from the private sector or founding agencies in France, so if you can just disclose that, so you can have an idea how you go from lab to startup in France in terms of funding for?
Yeah, so in France, so we have there's a lot of things which are complicated, but there's one thing that works, in fact, is trying to find early funds for startups. So for the first 2 years of startup, it was quite easy to find both state money. So we had money from the government, we had money from the local area, and on top of it, we had private investor, which was, as I said, Innovacom, investment fund, we say in English, I'm confused the names. So it's a company whose job is to invest into startups. So I'm not completely sure, but I think for our case, it was like 2/3 came from this kind of a private sector and 1/3 from the public one. And then, but because we already had an industry partner like Alcatel, it was quite easier to raise private money, because when they see there is a potential market already, they are happy to come in.
Okay, thanks. I guess we can take the last questions from Darly for Nicolas, and then.
And hello.
Go ahead, Darly.
Time is running.
And hello, thanks for the nice presentation. I was actually, when Gustavo invited me for this meeting, I was a little bit reluctant of accepting or not, because I actually work with optical communications, with space division multiplexing and algorithms for separating polarization and multiplexed channels. And but when I saw your presentation, I felt at home, and because I've been following also all these records and all this evolution with STM systems. So it's more a comment, and I'm still thinking if I fit in this workshop, but after your presentation, I feel more confident to proceed in trying to be part of this team working on this project on quantum technologies. Thank you.
Okay.
Okay, great. Thanks, Darly. I knew you would find your spot here.
Yeah, thanks for the comment.
Okay, I think now we can make a big Zoom clap for Nicolas' great participation, and he'll be with us all day. So in the afternoon, if you guys have further questions, I'm sure we can find him on the chat list.
Yeah, so I will be on the chat all day. I will not assist to everything, but I will be back for the brainstorming anyway, that's for sure. But I will keep the Zoom on, so if people have questions, I'll be happy to answer. Thank you.
Merci.
Okay, now we follow on our schedule. We're about 15 minutes to half an hour-ish late, but I think we'll be fine. The next speaker I'm very happy to introduce is Dr. Mian Zhang. Mian is co-founder and chief executive at HyperLight Corporation, which is a venture capital funded spin-out from Harvard University, whose purpose we're gonna learn from Mian himself soon. And I'd like to introduce just Mian with a bit of his background. Mian was raised and educated in the ancient city of Xi'an in China, which, by the way, is the home of the terracotta warriors, if you ever heard about them. He later moved to England to pursue his bachelor degree in physics at Bristol University, and then to upstate New York to get hold of his PhD degree in applied physics at Cornell University. Well, that's where I met Mian, and as he joined the group of my former postdoctoral advisor, Professor Michal Lipson, and I was very lucky to have the opportunity to closely work with him back then and later on as we kept our collaboration when I returned to Campinas for my professor position. Well, after getting his degree, Mian joined Harvard University for a postdoctoral position with Professor Mark Alonka's group, where he made breakthrough contributions developing compact lithium-ion devices and brought this technology to a whole new standard. So with no further ado, I welcome to the stage Dr. Mian Zhang. You were already a co-host, so you can start sharing your screen, Mian.
Oh, sorry. I think I have to switch and log in again. So maybe you have to enable the sharing again. Sorry.
It's fine. We wait for you.
I just did it, Mian, and I would also like to say it's such a pleasure to see you.
Sorry. Yeah. Oh, Paulo. Hey, Paulo. Good to see you too. Yeah. So okay, great. Can everybody see my screen?
Yes.
Okay, great. Yeah, thanks, Gustavo, for introduction. It's an honor to speak here. So as Gustavo was saying, I'm now involved in a startup at HyperLight called HyperLight, which is spun off basically based on my postdoc work that I participated in. So I think in today's talk, I will try to speak a little bit less about the technical stuff, and then I'll give a little bit background on technology, but I will try to focus a little bit more, I guess, on sort of how we got here from the, I guess even from the earlier days, and especially what we did from sort of my own perspective on how to go from, I guess I was back in the days when I was working closely with Gustavo. I think he probably knows that I had my mind very set on academia, but one thing lead to another, and now I'm full time in a startup company, and then I would say like I'm also shifting. A lot of my responsibility is there's still a lot of technical, but there's also a lot of new things for me to learn. So my slide, I think it's I think the way I'm hoping to approach this is that I will try to go over the slide relatively quickly, so I don't have too many slides. But then we can have a lot of time to discuss and then to talk about sort of the I guess the journey, and then my thought about how to, especially on the sort of the deep tech side, my experience with the technology translation. So our company is founded in 2018. So we are a startup focusing on commercializing ultra high performance electro-optic circuits. Actually, this part about what we exactly do, it's something we spent quite a while to figure out. But the main technology behind this is thin film lithium niobate, which I will talk a little bit more. So just to give a little bit of background on of the company, so our company headquarters actually are located right here. So it's between Harvard and MIT in Cambridge. I think as a result of the pandemic, so we ended up not going to the headquarters much, but it was our home before pandemic kicked in. So we are funded by VC, but we also have government funding, and then we have a lot of earlier customers that has sort of multiple sources of money comes in. So just to give a bit motivation on the on the work that we do at the company. So this is sort of a global network, fiber network picture I found on the internet just to show the complexity of the backbone network. So this is only for the heavy traffic in the oceans today. And if you zoom in, the sort of in the inland area, you not only have the fiber in the ocean, but you also have the terrestrial backbone fiber network. So these are essentially the analogy of highways for information traffic. And then if you go sort of zoom into one of the nodes in these fibers, and you will discover hundreds of thousands, if not millions, more optical fibers within sort of data centers. And this is all growing at extremely rapid speed. So if you look at the sort of the capacity of the optical transponders bandwidth, it basically follows the exponential trend, with the data capacity growing about 45% per year at an exponential rate. And this is mostly dictated by Moore's law as sort of, which is still going strong. And as we go to smaller and more powerful devices, the sort of the data we're pushing out them is also increasing exponentially. And so this trend is also observing optical fibers. But the very interesting observation here is that the fibers does not exactly follows 45% per year rate. It's sort of going faster sometimes than slower at others. And this is mainly due to sort of the nature of the technology breakthrough happens on optical fibers that that in the early days, sort of when the WDM fiber technology was out, there was a significant increase in the bandwidth, but then sort of there's a long, slow increase afterwards, as there was no sort of, I would say, like architectural change, but rather sort of slowly pushing the performance of each component forward. So what is the problem here? So the problem is basically we are at a point where we do have a potential mismatch between the rate of the fiber growth and then the rate of data demand. So if you look at, this is actually from a paper that is 10 years ago at 2010, but it's already predicted that the capacity of the fiber growth is going to basically saturates around around 2010. That's when this started, and then the demand will continue to increase, and then eventually there's going to be a problem around year 2020 because there's no obvious way of keep scaling optical fiber bandwidth, and this is actually now a pretty big problem. I think I was in part of the previous talk from Nicolas. There seems to be some very exciting development there. This is one of the possible solutions is to go spatial division multiplexing, basically using multimode fibers or using parallel fibers. But one of the key problems is not the sort of going with more parallel fibers is a good solution, but it still doesn't address sort of the exponential growth in energy power consumption. So if we take a deeper look on sort of a typical optical fiber link, so what the way it sort of works is it goes from an electronic domain processor into an optical transceiver that converts electrical signal into optical signals and then convert it backwards and then take it to another electronic processor. See, in this basic architectures, the optical modulator, which is the part that does the conversion, after conversion, electro-optic conversion, is a very important element. This device need to work at extremely high speed, and it also need to work at very high sort of data quality, fidelity, and at the same time, they need to be low cost, and also and also provide the data at very high quality. So this electro-optical interface, as I was saying, is everywhere that is in the sort of the clouds, which is the optical fiber networks, but it's also on the sort of the front end. There's also the radio towers, and then there's also the connection for a lot of sort of other forms of wireless communication that eventually all goes down to electro-optic fiber and then sending to base stations. And one of the very important thing here was that as the communication bandwidth increase, the sort of the base frequency or the analog port bandwidth of these different links are growing at an extremely high speed. So right now for data centers, the analog bandwidth is approaching 100 gigahertz. And then for 5G networks, the specification is up to 86 gigahertz. And then for space applications, it can sometimes even go to 300 gigahertz. So let's take with this fiber communication, which was the earlier example I was talking about, with sort of the data increase, the analog bandwidth of the optical ports has been going up from 2013 to about 30 gigahertz, and then to 2016 about 50 gigahertz. Then I think right around now we're at around a 70 gigahertz point. And then we're going to go towards over 100 gigahertz in about 3 years. So what is really the problem here? So I was mentioning that the power consumption is a primary limiting factor going forward in terms of growing the fiber bandwidth to the next stage. And so this is what I mean. So silicon photonics has been taking a lot of momentum in the last few years. in sort of to provide a integrated photonic solution to problems of electro-optic conversion. But if you take a silicon modulator today, and then which is, if you design it for 60, 70 gigahertz, what you'll actually find is that the electro-optic power consumption to do the data conversion is actually higher than bulk lithium niobate modulator, which is the technology that's incumbent for for the last few decades. And one of the reasons for this is that when for silicon photonics, the greatest advantage is that it leverages a lot of the tool set and then the expertise developed for microelectronics, so that you can easily scale the system up. But there's also limitations, is that silicon was originally chosen for electronics because its superior electronic properties, but for photonics, it was partly chosen for photonics because of scalability. So if you objectively evaluate if silicon actually is a best photonic material, especially for electro-optic conversion, the answer is probably not, because even with the miniaturized silicon modulators, when you compare it with the bulk lithium niobate, which is a very old technology, that is actually worse, and then this difference is only going to be exacerbated for higher bandwidth. But don't take me wrong, this is still a great progress, because this plot is one-dimensional. We are only showing the power consumption, but there's also the element of cost, which silicon has addressed this significantly, that the cost of the modulator is much, much lower. But either way, the power consumption here, this is only the bandwidth of a single port. So with the growth like this, it's unsustainable for the next generation solutions. So at HyperLight, sort of what we did is basically we have a solution to address this issue of very costly solution with 70 gigahertz, and then there's basically no solution beyond 100 gigahertz, because at that frequency the power will be completely unmanageable. And what we did here is that basically we showed that if you have the right material, and then you have the right fabrication, that you can achieve performances that is completely in a sort of different realm compared to the incumbent technology. So this line at the very bottom of the graph, this is actually the projected energy power consumption. I actually measured in some of the data here. That's what we can do when you have the integration with the right material. So I think in some literatures, the lithium niobate is sometimes referred to as quote unquote silicon of photonics. It was mainly to say that, to point out that if you were to design a photonic material from scratch, or if you were to choose the best electron photonic integration material from scratch, the lithium niobate is considered one of the top candidates that have the sort of the ideal properties for integrated photonics. So just sort of very quickly on the technological breakthrough. So this is the majority of the work was done at Harvard. I think I joined the group in a pretty exciting time that there was a lot of material research done over the previous years. I was very fortunate to join the group and push this technology, helping to push the technology to the next level. So we had quite a few, I would call this pretty successful papers coming out in the last few years. And this is a result of sort of the breakthrough in a manufacturing or fabrication of this chip on I would call it on a pretty consistent level. And then once you have that, you can, you have the basic element of of electro-optic conversion on chip with very low optical loss. And once you have that very, very basic component, it's quite, there's quite sort of, we push the work quite a bit forward just to demonstrate the power of once you have that, what can you do? So for example, in the modulator paper, what we demonstrate here is that we basically show that you can achieve lithium niobate modulators, but then you can drive the modulator with only a CMOS driver, as opposed to power hungry using very expensive electronic amplifiers. Then there's also frequency comb generators. There's also other elements that are we basically show potential for communications, but there's also, I think, one of the key topics in this discussion is for quantum. So I'm happy to go into any of those sort of application areas, but as a company, we must have a primary area of focus. So that's, as I was mentioning in the beginning, the electro-optic modulator is the one that makes sense for us from both technical and market perspective. So just to compare here to highlight sort of the technology compared with existing, and then I guess there's also the upcoming technologies. I think, for example, as a silicon, I think the biggest advantage over silicon is really the performance. Silicon still have a lot of the advantage with material stability. I think the yield is the scalability, and then but with it's sort of I think when you think about the electro-optic modulator, it's one of those issues that it's better to have. It's that you need to have every single performance metrics here checked, because in a sort of a very practical environment, these any of these study bits, it's not good. It's pretty detrimental for the sort of overall system level performances. So just to pick one example, for example, silicon organic materials, which is electro-optic modulators made by spinning polymers on top of a silicon photonic solution. It's very elegant way to solve the problem, because if you could spin on a material on an existing CMOS process, then you can still leverage the low cost, but at the same time you can provide excellent performance. But one of the sort of the very active research in this community, and actually this has been sort of the case for the last decade, is to improving the material stability, because that's sort of one of the main challenges for polymer, and it's one of the main obstacles for that to be used in many practical cases. So I think this is one of the sort of the very interesting combination for lithium niobate, that it has a lot of this new exciting performance advantages from a new fabrication and design perspective, but it is also a well proven out material in terms of its properties over the last decades in the form of bulk crystals. So that's kind of a very nice combination for new material, that it doesn't have as much as a high barrier for a lot of new materials when in terms of commercialization. Just to talk a little bit about the sort of the company's offering right now. So we already shipped products in terms of chiplets. So these chiplets, they are basically electro-optic modulator chips. They can actually, I would say it easily goes over 100 gigahertz, which is very rare, I think, in terms of or very difficult to achieve on other platforms. They easily go to 100, and sometimes we have customers testing this over 300 gigahertz while still maintaining a pretty low voltage. And then on the other hand, you could also configure the modulator to perform ultra low voltages. And then we have customers from many different sectors, actually including quantum, that are using these modulators to achieve sort of different things. Just as a product, we also provide sort of evaluation kit for the modulators, which is easier interface with optical fibers, and then a lot of customers prefer this sort of form so that they can actually test this in a slightly more complex environment, or in a more complicated system level. And at the same time, we are also offering multi-project wafer runs. So these are basically thin film lithium niobate chip and devices. So it's very similar to a silicon photonic tape-out process. But I guess I definitely want to emphasize the difference here is that for us, it's still a little bit early stage. So the tape-outs is, we don't have as developed PDK as silicon photonics, but one of the key advantage here is that we have a lot of flexibilities in terms of customizing the circuits with reasonably low cost, and then our turnaround time is very fast. So sort of, I think this multi-product wafer exercise for us is very important sort of in two aspects. One is that we don't want to get, because this is still a relatively new material and a new process, we still want to show that this process is fundamentally scalable. And then second, that we want to be work very closely with customers in terms of figuring out and customizing the photonic integrated circuit solutions for their particular applications. So it's very important that that we have this customer engagement. I believe that is the end of the technical part, I guess, quote unquote technical part of the talk. So if this is okay, so I think I would like to move to I guess a little bit more discussion. So if that's okay, so we can do I guess I will probably ask Gustavo. So we can do Q&A, or if, I mean, I'm also happy to pick on a topic and then just go from there and then talk a lot about it. I think there's a lot of stuff in the slides that we can expand on.
Yeah, I think it's up to you, but I think was great. We can have an idea already of what HyperLight is pursuing, and maybe I can start with a question towards the quantum applications, and you can probably evolve that with the startup. I think a lot of people are curious about the startup process. I have the feeling that your route is quite different from what we learned from Nicolas, in the sense that you are in this sort of startup environment there at Harvard, right? And there's no big company involved, as far as I can feel from your talk, right? So you were really starting from scratch, and of course, funding to go there. There was not the initial interest for the company. But I'd like to point, because you sort of contrasted the silicon versus lithium niobate, right? And of course, that's a natural question, because silicon is being pushed as this new low-cost, large volume data communication platform. But as you mentioned, it has several issues to be solved. And if you're targeting at a market that is looking for those properties like low cost, large volume, of course, it's gonna be a tough fight, right? If you can frame it this way. But if you're looking at niche markets, and then that's where I would like to bring quantum. Like if you want to have, technology for generation of squeeze states or single photon sources through parametric down conversion, and or other quantum sensors in a way, how is the company looking in these directions? Do you have like how can you comment on that?
Yeah, so okay, so great. So I will just interpret this question as a more about I guess even a market interest strategy, and then sort of how do we balance, or how do we think about the niche market versus the sort of mass market, and then also in particular about quantum. So yeah, so this is a very good question. This is actually the exercise that we went on a lot in the very beginning. So first of all is that we actually do have a lot of customer interest, including from very big companies. It's just like we have NDAs with this company, so we're not disclosing it here. But what I can say is that the problem with silicon photonics, or at least with the modulation side, is pretty serious. And the willingness, the amount of willingness from the big companies to looking for new solutions that can solve these modulator problems is quite a lot. So I'll just say, like, what we typically read from the papers on the perspective is very different from what the customer actually asked for. For example, we would imagine the integration. Like, for example, I'll just give one example here. Do you have to integrate the modulators with every other component, with the lasers, with the detectors, with a lot of this component? If you read the paper, it looks like that's a trend. But I can tell you from our interaction with the customers, it does not need to be the case. There's a lot of customers even planning several years down the road. These are big tier 1 customers, several years down the road, that their outlook vision does not have to involve that, and they're completely okay with with lithium niobate or with any other materials that being a separate component. It's because the project is a system level project, and there's always pros and cons in terms of integration or not integrating. If you try to integrate everything, you're really limiting yourself to a lot of functionalities and then to a lot of issues. So I guess just to circle back to the question is that we do think that this is a very important. This can be a very important solution for even the large volume markets. For example, like a frequency beyond 70 gigahertz or 100 gigahertz, because there's actually no alternatives. So that's the case here. So it may take a while. Yes, it may take a while to reach those sort of maturities, but we do believe that it has that potential. So now going to the second question about the niche market. Yes, so that is still true, and it's still a very good point, that especially for the it's this material, they're sort of the stacked problems. You have two sort of problems to solve here. The first one is that it is a new material, so you got to figure out how to make it. Then the second problem is you got to help the customer to translate your solution, because your solution is part of the puzzle. You have to shape that piece to fit well with the rest of the pieces, and you need to figure out with your customer with the application in mind, and then tailor that into their specific requirement. And that is, both of these are a lot of work, but of course, if you do get them, then that's a pretty successful outcome. So in terms of we're also a small company with the people around 8 to 10. We are focused on I think at this point on a sort of modular, because that's still the core element. We do have through as these standard products I was mentioning, that we want to provide a community sort of a wider support. So we do have customers in quantum, but the way sort of we approach it is that we focus on devices, and then for most project related to quantum, we have the customer basically going through this multi-project wafer run, where we would tell them the specifications and how you would do it. And then, they would tape out the chips, and then they would measure it, and then they would, change their designs and then try to do tape out again. So it's a little bit like, I guess, a pure play foundry there, that is in terms of quantum. But in areas where especially high speed or low power electro-optic solutions needed, we typically can provide more insight into that, and we very rarely find customers that want to design their own modulators, or they're okay, they're completely fine with just purchasing whatever we designed, because it actually saves them time and money. But in terms of sort of going down the road in future, we have to see how this evolves. I think that it's probably that there's two directions, or this sort of for quantum and then for classical, that they would have to be split, because these are two different business models. And then there are two different focuses, because one is you're focusing on flexibility and then focusing on design. The other one you're focusing on sort of volume and then scaling up. But I do want to say, like, this two directions, they will split, but they will come back again, because one of the things I think, especially for quantum technology, I mean, if you look at lithium niobate as a researcher, I think I wasn't. I think actually in my undergraduate days, I was also involved a little bit with quantum architecture. So I'm aware of some of the challenges there. The lithium niobate is a pretty ideal material, I would say, to do a lot of experimenting in quantum. For example, it's very low optical loss. I mean, this material, the fundamental loss is extremely low, less than 0.2 dB per meter. So now with the etching, I think we can get to 3 dB per meter, but I'm sure there's a way to push it for more. But at the same time, you get very high switching speed and capabilities, and then you also have second order nonlinearity for photon generations. You can generate photons, switch them very fast without optical loss. And there's also a lot of work recently, I think, from a couple of groups that is integrating superconducting photo detectors on this platform. So there's really a lot of possibility, but the issue is someone has to set up a scalable sort of fabrication for this material, so that the researcher can actually focus on what is important, what is valuable is the design, and then the sort of the architectural breakthrough given the property. You know, if there, I think it's too big a problem for anyone to take on if they have to do device design, material research, and all the quantum part. So I think probably a better way to look at it is that the classical market is a great market to leverage to push this material into the next level of maturity, and whereby, you know, it can provide very exciting solutions for new applications like quantum. And it's not, and I think this is a lot of new technologies, I think, for quantum do not have the sort of the privilege that it can leverage a big market in a classical side. And I personally do believe that is a pretty big obstacle for a lot of new emerging quantum technologies.
Okay, thanks. I guess I'll not try to dominate the discussion here. And there's Marcos Martins with his hand raised. Please, Marcos, go ahead.
Thank you. Thank you, Mian. Congratulations for your company and your success.
Thanks.
You are established in one of the most expensive square meters in the world. So I would like to know, how was the financing of your company? How did you scale the financing to achieve this success?
So yeah, that's actually a very good question. So this is something I think, as just from sort of my own experience, I think in the very beginning, I guess all of our founders were very naive. We were thinking, oh, you know, let's go out and raise some VC money, because that's what we read on news. Some company raised 5 million, some company raised 10. And then we did go out and we did raise money, but we also, at the time, there was someone, you know, we got advice that was basically, you know, it may not be as bad as what you think if you grow this organically, like sort of bootstrap your company. And yeah, so I'm actually happy to talk. I think this is a little bit related to what Gustavo asked about. It's also really depend on your market and your go-to-market business strategy. It's not that one way is better than the other. So for us, it's actually quite a bit of mixture. I think we raised a bit of VC money, but we didn't raise too much. It's actually, we didn't even try to raise too much, because the moment we raised, we actually started to realize we ship devices right away, and then we actually generate pretty significant revenues, and then it's covering ourselves out. And then there's also option for government funding, but just to give sort of my experience on these two fronts. So initially, I think I was very naive, think like, you know, you have to raise VC money to do something significant. So that I think it's a double-edged sword, because the very important realization is that I think VCs, they have their own, I guess, own sets of priorities, and then they have their visions, and then you need to work with them and then to make sure your visions are aligned. And it's not good that, you know, like that if you and the VC does not see the same picture, even if you think that or if you think like, okay, maybe I could try to compromise, or if maybe this is a detail that we don't figure out, but if you feel there's something not quite work out, and even if you get the money, it will be a bigger problem later on. You know, for example, VC may want you to hire as fast as possible, but the thing is, as a technical person, you will think, okay, my technology is not ready. If I hire this as fast as possible, I'm gonna burn cash very, very quickly. And then you have to raise more and more, and then, you know, there's always the terms come with that, which you have to chop off part of a company, and then, you know, eventually you have to. So that's one of the drawbacks we see here. So then there's the question about bootstrapping. Then bootstrapping is basically you make profit as you go. You keep the team to the right size, and then and you grow it organically. And then I think your team is really the driver's seat for your own company, and that's really, really nice because you can do whatever you want, literally whatever you want, of course within the context of law. But you can do research, you can do customer service, you don't have to justify for any of our targets as long as your own board and your own employees are happy. So that's sort of I think the benefit. So we are sort of in a mixed model. And I have to say, like, our founder, which is a public, is Engine, so which is a private VC fund, and with MIT, was funded by MIT, actually, the VC board. So it's a non-traditional VC in the sense that they have a very, very long investment horizon, like what's 15 years or something. So they are not in a rush to get their money back. And I can tell you that is extremely, extremely important. Because every time I ask them, like, for example, there's a question like this: should we go into quantum market? Should we go into mass volume market? If you ask this question to a traditional VC, they will be like, wait, are you crazy? Like, you already raised money from me. Like, why are you even asking this question? Like, you should be doing whatever the market is the largest and whatever you can scale up. But what our VC was basically saying is that, do whatever makes sense for you. And then, we're patient, and if you want to go to quantum first, that's fine. If you think you're ready for mass volume, we're there to support you. Like, this sort of very unbiased opinion, that is extremely important, because VC, they have money, so they're really in a power. They have power in their hand. So even if like a hint from them, the founders are likely take it very seriously, especially for the first-time founders, because the VCs are really the boss there. So in that sense, I think we were really, really lucky. But there's also issues with other sorts of funding, of course. With Bootstrap, you are always at stress. You have a very high stress level because you have to deliver, you have to make the customer happy, and then I'm just saying, like, this is the case, always the case. There are some customers that are particularly challenging to work with, and some of those interactions can be very draining. But of course, you're a company, so that's what you're supposed to do. But if you also have money problem burning on your back, that's going to make your life pretty difficult. And the VC doesn't have this problem because you have someone with deep pocket, and then you're good for a while. And then the last one is government funding. Government funding is great. A lot of times it's actually a reasonable big chunk of money. It feels like it comes for free, but it does not, because you have a lot of reporting duties and taxpayers' money. So you can't really spend on money that's the things that you think would be valuable without justification. So that's the case. I mean, I think that's I'm probably just being repetitive because I'm just telling the very obvious truth that there's no free money. I think the answer to answer your question about I guess how we do the funding, or how we think about it, I think it's the final answer is just do whatever makes sense. Don't try to you don't need to be very hard on it. So for example, if your technology is a mass volume market, you will easily find VC funding or VC that is willing to support it. It doesn't have to be mass volume. I guess quantum is one of the areas that is pretty hot recently, that because it has a huge market outcome if it's successful, despite that it's being quite challenging. So that's also fine. That can be VC supported. Or if you have a technology that customer want to pay today, but you don't know how big it will become, and you think that taking this a few years in the driver's seat is better, so then you can do customer funding, and then you can do a combination of these three. So yeah, so anyway, so that's the case. I guess you could also vary quite differently for different country. But at least in the U.S. or even in Cambridge, in Boston area, that's sort of the options we have here.
Okay. Thank you. Congratulations again. Very nice job. Work.
Okay, thanks, Marcos. I guess the next one on the list is Felipe Barbosa. Please, Felipe.
Hi, Mian.
Hi, Felipe.
What I was about to ask, I hope something fast, quick. It's about these multi-project runs. And actually, I want to congratulate you. It's a very nice presentation and very nice to see like where did you where you get and where you're going, right? It's really cool. So I want you to talk a little bit more about this multi-project runs. You know, you have like some plans for having these. I looked it up, tried to see in the website. I couldn't find it. So you have these. About that.
Yeah, sorry. Yeah, actually, the website we're planning to update it's a bit outdated now. So we gonna the multi-project wafer run. I think we will have this, this available in the foreseeable future. But in terms of how we work with the customers, so we have all the very basic components like grading couplers, like wide splitters, directional couplers, all of these components, and then I think at the moment it's really depends. We were thinking about building a PDK, which is still on our radar. But the issue with the PDK is that this technology is still relatively early comparing with silicon technology. So there's still a lot of changes that's going on, and this is actually good for some of the customers because if you have a PDK, you're pretty much stuck with whatever the material stack is. And this material is also super broadband, so there are some customers invisible, and they use completely different material stacks. So anyway, but we do have a sort of a base guideline when we interact with the customer, like the wafer film thickness, edge thickness, and what components are available they don't have to worry about. And then normally this, because of the relative early stage of this project, normally the circuits are not super complicated to lay out. Because we normally take this and then get some of the key components first, and we can go from there. So it's up to specific cases that we normally work with our customers to figure out who is making it's really depending on what it is. For example, if it's electro-optic modulators with some sort of standard components, then the customer can just describe to us what they wanted, and we can actually come up with a design, and then the customer can approve it before we try to make it. Or some customers, they are very, very experienced with designing photonic circuits, so they just ask for index, ask for the waveguide geometry or the fab capabilities, and then they do all the design themselves. Of course, with our input on the layers, so that we can actually make them. So either way is fine for us. Yes. And then there's passives and actives. Active meaning there's electrodes, and then the passive just meaning optics, but for a lot of, you can still do a lot of nonlinear optics on a passive platform.
Okay, thanks.
Okay, I'd like to bring in some of the questions that are being posted on YouTube, and perhaps also apologize a bit because I think there was a question we missed during Nicolas' talk, but we'll forward to him so that during the afternoon session he can reply. But this one is directed to you, Mian, from Natalia Tomasio. She thanks for your talk, and she would like you to comment on your transition to the company and what factors motivated you to switch to the company environment. And also, if you did it as soon as you achieved the breakthrough in the lithium niobate fab.
Yeah, okay, yeah. Thanks for the question. So, I think for me, if I personally went a lot of back and forth in this sort of mental exercise, and I think the overall conclusion is that I feel like I did the right decision for myself. So I didn't actually doubt if this was the right choice. I think 2 years into this, so I think that's a pretty good sign. But I think from the early days, I think when I was with Gustavo in my house group, we worked on optomechanics, which now it's pretty fundamental research there compared to the sort of the project that we're taking on now. And I have to say, I really enjoyed it. I think today, even when I think about it, I still I like many aspects of that project. So that's why I continued into Marco's group. But actually, when I joined Marco's group, I know this in Orbit. I heard about this word, but I don't know what it is. And then I was actually planning to do something related to bio as a postdoc project, just to try to find a job on a two overlapping hot areas. That's sort of my thought at the time. But I guess one of the other very important person in this innovate, Chung, he was a postdoc. He's now at a city university in Hong Kong as a professor, but when he was a postdoc, Sorry, when he was a PhD student in Marco's group, he sits right behind me. And that's that's all that's how all the scientific research started. And then I was like, okay, I was in the house group. I know like modulators looks important. I don't know why it's very important, but it seems to be a hot topic. And then lithium seems to be like a modular material. Let's try to make a module. That's how it's very simple. It's as simple as that. So that's how we started. And then I think when we got the first results, which was we had a lot of difficulty actually publishing that results. But I think one of the things, and we're very thankful for this very important feedback, is at the time we got Professor Joseph Kahn from Stanford, who learned our work, I think, in conferences, and he was saying like, this is great, like this is I think he probably put it in a very strong way. He said, this is it's much better than the silicon solution. So that's sort of what we are really surprised about with his comments. We're like, oh, wait a minute, like why is this much better than silicon modulator? What's the problem with silicon modulators? I think that's sort of the very early attitude we had, was that we were trying to educate ourselves why our work was good. So we asked the professors, like, why do you think our result was good? And he told us all about the stuff like I was mentioning about power consumption, data fidelity, and all of this practical aspect, which, that's, I think, the very first part that it really excites us is about about learning the actual problems that we're solving. Then the second part is, I think that when we, after then a couple of years, a year or so into the project, we went to the conferences and then presented this result. And the response from people was very different experience for me. So, because I did present it sort of fundamental science research, and you will see like, everybody was very nice to you. They will tell you, hey, look, like, your research is great. It's fantastic. It's very interesting. But when we presented this result, we have people coming in basically were asking, how can I get it? Like, where can I buy this? Like, I need this on my bench. Like, can you help me with that? And that's a very different experience to me. And I think from a personal level, I feel that's the work is very impactful. I think but at that time I didn't sort of change the mind yet, but I think that's the, if I look backward, I think that's the part where I was very, I think that's a very important reason for me, is that I feel like I'm making a higher impact. And then so I think that's more, a little bit more about the projects. And then I think then we are at the sort of the branch of deciding, because I think I had a pretty good postdoc careers in terms of papers. So I think that was I was hoping for, and I think I got it. And then I think that was in a pretty good position to apply the job. I actually ended up not applying anything. I just go straight full-time into this. So the reason is so this is when how I thought about this. In a decision-making moment. So I think at the time I was basically asking myself is what is my goal? I think my goal there was that I do want to make an impact. I guess maximize my impact as a technology, to bring new technology to help people to solve problems. And then so that you can do that as a research in a research institution, or you can do that as a technology startup. Both ways are very good ways to do it. But I think at the time for Lithium Elevate, this particular project, first of all, Marco is still very active in the field. So if I go into, I don't think I would be competing with him, but there's that sort of overlap there. And I think at the time we see an opportunity that there's problems that only a company can address, and that particular example is right in front of our eyes, is this multi-product wafer. This is not something a university can take. So that's sort of, I think at the time what I was really excited about is not just the modulator, it's actually the whole platform. About building this infrastructure that allows you to do different things. That idea excites me a lot. And when I think about how can I do that idea, university is not a place. For two reasons. One is that I think as a research institute, you're not really supposed to do commercial activities, which is this multi-product wafer does require. And I think a second very important reason was actually, I was just literally thinking about how exactly am I going to do that? Because I need a fab, and then I need to train people to work on it. And then I need and it's definitely not a trivial business. So, and then we have the working process right here. So I was also thinking about what is the quickest way that we could get started. So that's one of the combination. And then for myself, I think like I was asking, I'm beginning up, I guess, my career plan for the last decade that I was planning to do to be in academia. But I feel like at the time, as long as I'm doing the work that I feel that it's contributing to the technical side, then I would be pretty happy. And I think now 2 years down the road, I would say like I'm still pretty happy about my choices.
Great. Yeah, I think the beginners will love to hear that this is a route to go. That's what we want to foster in this initiative. That's, I think, a big thing missing in Brazil. I was in China last year, and actually I saw that this startup thing is really kicking out there too. And I think we need to catch that train. That's for sure. There's a question still raised here. I think it's Thiago, and we can start probably directing towards closing because people might have other duties for the lunch break. And I think I can take this last question from Thiago Alegre. Thiago.
Hi, Mian. Great talk.
Hi, Thiago.
Thanks again for your insights. So I want to go back a little bit on the quantum, and actually not on the theory about quantum, but on the environment that you just you grasp at the end of your last question that you answered. That is basically like the university is not the place to do your business, but is the place in the sense that there's this environment where you can raise your company. Mm-hmm. So specifically in your case, you need a clean room, and it doesn't seem that you have a clean room in your company yet. It's too expensive to have a clean room for yourself. So I just want you to comment a little bit on how you foresee having like a quantum business detached from universities, first of all, and how at the starting point you need to be closer to universities to grasp their environment and also their capabilities, like for example lab, and in your case for sure like microfabrication.
Sorry, so you're just trying to understand the question. So you're saying like, can you just? I didn't fully understand. You were saying like, I understand the part you were saying about the we're relying a lot on the university infrastructures. And what was the question?
Yeah, so if you are relying, so that's the question. If you are relying now on the infrastructure of the university, and what kind of infrastructure do you believe is essential for building quantum business?
Oh, okay.
There is on the university that you still don't have a company yet.
Yeah. So so this is another question that I'm just happy to talk about. Like especially I think for a lot of the new material, I think quantum is definitely. I was talking about silicon as for classical. There was a challenge with silicon even satisfying classical communication requirement. I think for quantum probably even more so because for quantum, you need more functionalities. And I'm just saying like the university resources is still a fantastic place to start because it's there's a lot of stuff I think as students probably we don't appreciate that. The university set up all the infrastructures, you're working there safely, the legal problems are taken care of, you don't have to worry about a lot of things. These are a lot of the, like you open your own lab, these are all the stuff that you need to worry about, like outside of the university environment. So I think there's a lot of benefits to leverage university clean rooms. And then I think about this question about, or just the way I understand it is like, do you need, or maybe another way to ask is, do you need to have your own facilities to do quantum, right? Is that another way to phrase it? or how do you see like you have your own facility through quantum? Is that correct?
Yeah, as far as I understood from your talk, like initially you need to be close to university. So even like Marcus mentioned that you are the most expensive square meter, but yeah, I guess that you are there because you have like the two big universities and MIT, which is MIT, that has all the infrastructure for microfabrication, which is needed for at least for most of the platforms on quantum computing. So I guess my question is, okay, you need to be close to university because they have like this facilities, or it's just like a business choice for the beginning?
I think it's both. So first of all, you can, and there's definitely examples where you can spend early capitals to build your own clean room, to build your own your own lab and your own facility. And but I just want to give a warning for that, because you really want to think about what do you want to spend your first very important money on, because just one thing, because in a university we're very used to do everything ourselves. We're doing fabrication, design, measurement, everything, writing papers, everything ourselves. But managing a production facility is nothing like what we are experiencing in a university. I mean, that's exactly what I was saying. The university is already taking care of a lot of the stuff like for you already. So let's take this one particular as an example. The way sort of we think now, lithium ion, but even with sort of the market prospects and the potential applications, we still think at least for a while it's reasonable to use the university cleanroom, because it satisfies our purpose. We can ship devices to our customers as early product samples, but it's good to some point where either your yield requirement is so high that you cannot tolerate the process control in the university, or your customized specific volume need that you need to solve. But one thing is, when you start to solve this problem, when the need is there, when the market is there, it's not just you. You're gonna find people that's willing to help you, and then you're gonna find the people that has spent their career in fabrication, and then they can take this project and do it right in the first time, rather than you try to do it yourself for the first time. I think the question you got to ask yourself really is, what is the value that you're bringing? Is your value fabrication, or is your value design, or is your value on a system level or architecture? Because we do a lot of fabrication ourselves, so we may think like our expertise is fabrication, like in the case of lithium ion, but it's actually not. Like fabrication is TSMC, is Global Foundries. That's fabrication. Like there's so much, how to manage it, how to do it efficiently, still maintaining good costs. We are just users. We're users of those facilities, or we're not the sort of the, know how to manage the facility ourselves. So our value adding point is the design, and then actually, sort of is the design of that. And the fabrication is a good knowledge for us to do it. So, and then if you think about the quantum market, like our expertise is not even in the quantum. So we understand a lot of the challenges for quantum. So that's another differentiation. So for example, we would love to have someone from the quantum work with us, and then they don't have to worry about fab designs. They don't have to worry about exactly how to translate their quantum architecture into, like how wide should the waveguide be? That's not the question they should be worried about. Or they should be worried about if that's something that is doable in a fab. That's something that we worry about. We discuss the requirement, and then we simplify the work for them. So it's like in the verticals, we're in this layer of interfacing. I think for the quantum world, we're interfacing the fab capability with the customers. So right now, I think university is enough for the whatever our customer currently asks for. But down the road, as these scales goes up, then we definitely need a foundry. But I just want to say, do it yourself is still an option, and there's definitely a lot of advantage to it. But that you do need capital, and I think more important is that you do need a market demand that justify those expenditures.
Okay, great. Well, since we are running a bit late on time, I would like to thank you, Mian, for sharing with us your insights and this outstanding work that you guys are doing there. We're gonna cheer for the success of your company, and I'll certainly send you a message to apply for that evaluation kit. I want to have one of those in my lab. Anyway, let's send applause for Mian.
Thank you.
And of course, I know you have duties in the afternoon, but if you find some free time and want to squeeze in for any discussion, you are, of course, invited. And yeah, I hope to see you soon. And thank everyone for attending this morning session. Of course, Paulo, Marcelo, Fred, and Celso, if you want to make any comments, you guys are welcome. But I'll leave my big thanks for everyone that joined us both in YouTube and on Zoom. And at 2:30, we'll be getting back here for hearing Vanderlei Bagnato and then a brainstorm session.
Thank you.
Okay, thank you all. See you very soon. 2:30. Okay, bon
Thanks,
appetit.
everyone.
Bon appetit.
Good lunch.
Tá. Espera só um instantinho, deixa só o Malu dar o sinal verde pra gente que tá passando no YouTube.
João, você já escolheu?
Ao vivo tem essas coisas interessantes.
Isso.
O YouTube ainda não, pelo menos aqui no meu stream, ainda não tá...
Ele demora um pouquinho para entrar. Mas, Vanderlei, tem essas coisas interessantes, agora... o fato de que a gente está entrando na casa de todo mundo.
Ok,
bem-vindos à minha casa. Ok, Felipe.
Bom dia a todo mundo. Na verdade, não preparei nada aqui, mas todo mundo conhece o Vanderlei Bagnato, ele é professor do Instituto de Física de São Carlos, agora diretor do nosso Instituto, e vai agora falar sobre startups no Brasil, os desafios que a gente encontra aqui. Vanderlei, você pode...
Okay, Philippe, thank you very much. Okay, so I appreciate the opportunity to speak a little bit. I want to see if I can upload my presentation. Okay. Is that okay there?
Yes.
Yes.
Fine. Okay, so when I got the invitation, I thought I should speak about some quantum system, things that I do. But then I realized that I have to speak about startups. And in fact, I don't have any experience with startup in quantum information. What I do is in optics, with some relation, if we depend how you look, with startups. So around our institute, we, along the years, it's not 1 year, many years, there are like 70 or 80 startups in the field. From those 780, I will say that today, really established, we have about 46 to 50 companies working with technology in optics, from components to devices, and for different applications, or even spectrometers. We have a young company that are doing a spectrometer for machine learning, spectrometers that can go inside and collect the signal, and for the food industry and for fermentation. Because as you know, Brazil wants to play an important role in fermentation. So they need things that goes inside the fermentation tank or chamber or whatever. So this is my experience. So I hope I don't disappoint you. And what I was thinking in the first plan was, okay, well, let's talk like we do here in Brazil, we say a table of a botequim. But then I said, well, I mean, this is a good opportunity to elaborate a little more, maybe place some ideas. In special, because now we have one unity of EMBRAP. EMBRAP is a kind of institution on the federal government, but it's a combination of a private and governmental institution with finances, innovation initiatives. And then after I got this invitation, I consult EMBRAP because I have a decent amount of money to invest in things that are promising, but has to be with companies. And then I will explain at the end this initiative, which I believe so much in things like this. And I don't know if I'm the oldest one in this room, but probably I am. Oh, Rio's a little older, but not too much. So I decided to explain to you those ideas, because I know that here in São Carlos, at least, there are many people interested, and maybe we could reserve some spots of startups for exploratory ideas, but has to be in a different way. I'm going to explain to you, which is a new idea we have. Is more like the Fraunhofer type, which is translational. The things stay in the university and in the institutes for some time before really became a company. Okay? So I'm going to explore a little bit of everything. If I know that Paulo is the chair of this, so if you decided that I'm being so boring, you just give me a warning, you know, I can change the subject anytime. Okay, so I want to start to tell you a story. Everybody knows about the story of the elephant and the snake? Philip, do you know? No, Philip doesn't know. Okay, the story of the elephant and the snake is the following. You know, in Brazil, we always call young people either Joãozinho or Antoninho or whatever, because we have this is a common name. So the thing is, Joãozinho went to the elementary school. And in the elementary school, the teacher said, look, to all the students, you have to prepare a description of an animal. And then, you know, and I have this collection of 21 animals, and I'm going to make a choice here. So please prepare for all. And then I'm going to make a choice, and I hope you're ready to explain and make a good description of one of the animals. Okay, so here comes Joãozinho, and then he prepared about the snake. And because Joãozinho was a little lazy, he only prepared the snake. He should prepare a little bit of each animal, but he prepared the snake. And during the choice, in his turn, the teacher selected the elephant. And then here comes Joãozinho telling the description of the elephant. And then he started by saying, look, the elephant is a fantastic animal, big, very important in the animal kingdom. And he has big ears, so he hears very well. He's strong, so he's the support pillars of the forest. And he has a long nose and looks like a snake. And speaking about snake, let me tell you more about snake. So basically what I'm going to tell you the story of the elephant with a snake nose. So in other words, I want to use the opportunity to tell a little bit more than the topic that Paulo and Marcelo, I think, I don't remember who really asked me to speak here. Okay, now when we speak about quantum, we get all confused. You know, we all study quantum mechanics the whole life. We did our PhDs and our career in quantum mechanics in related topics. But then today, if we go to the internet and look for quantum applications, we get a little crazy because we are, you know, people already appropriated of this name. So, you know, I found that quantum physics proves that that is an illusion. And there is a health, quantum health. Oh, by the way, this one I found very interesting, which is a couple quantum. And then many other things is going around. But I found one that's very interesting. They say that using quantum physics, you can do good business. So more or less, this is the spirit of this, right? We advance the quantum concept. And then I went to read a little more careful, and has nothing to do with what you think it is. But anyway, it makes quantum seems to be in the everywhere. And if you look careful, that is everything quantum. You know, I remember when the electricity was invented. Oh, I was not there. But if you look at the history of electricity, after electricity was invented, people named electricity everything. Electrical soup, electrical shower, electrical dressing, everything was electrical. It seems that we're going for quantum now. But of course, quantum mechanics is really became important. As you know, there is a full biological understanding of the fundamental effects based on quantum. And I start a laboratory now here, which is to see this process that you see in the bottom. We are able to isolate a single mitochondria from cell, and then we send the photon by photon, and we want to see the ATP production. Because people do not understand exactly all the quantum aspects of this. And of course, people claim that really quantum coherence and everything is very important in the energy transfer in those processes. So you see, it goes much beyond the transferring information on the quantum application or making calculations. Now, this I saw today that I think Paulo, I was seeing his presentation. It seems to me that he used the same picture. You know, quantum technology, what's involved in quantum technology. But I think, you know, on the top left, you see that science in quantum is very important. It's one of the fields that cannot exist by itself if science stops to be advancing the field. And then I found, you know, this is not my picture, it's a picture that seems to classify everything that's important in this quantum technology. And I can more or less recognize people in this audience that are doing different things here. You know, quantum materials, you know, we know that there are people in this nano fabrication and stuff. They are doing very interesting things. Quantum sensors and clock. I know Philippe well, that he wants to do sensors, especially for gravity and maybe others. And I know Euclides that wants to do biosensor based in some of these properties. Encryption, quantum software. Here is a possibility because as you know, we have more theoretical groups in Brazil than experimentalists. And then that may be a good opportunity for this. Quantum computing, of course, is basically in the top. And others that is not listed in here. But all the science comes before the technology. And then, of course, I put it here in the bottom that we cannot make technology or a startup if there is no market for it, right? This is, I'm gonna get to this discussion later. But quantum optics, as far as I know, what is more expressive in Brazil, I think is more related to quantum optics. Even though I know there are many initiatives, I'm gonna tell a little bit, but quantum optics is being I would say a well-established field in Brazil with experimentalists in many institutions and also theoreticians. We have important contributions from Brazilian theoreticians in this field. And I think this is one essential instrument maybe for the quantum information and quantum communication. I listed some of the things from my head. I know that the state of São Paulo, all the institutions of, and I apologize for the ones I did not list, but then I put a map of Brazil here saying that basically in any state, I'm not gonna say any institution, but in any state you have strong groups doing something related, but there are some important players in here. You know, I remember Universidade de Minas Gerais from the past already making good contribution in the quantum optics. Of course, Federal do Rio de Janeiro, as the institutions here in São Paulo State, and many others. You know, I saw many people in the morning from institutions from Rio de Janeiro, not only the Federal do Rio, but the Fluminense and others that are deep involved with this. So, and it's not by coincidence that the leaders in this proposal or in this initiative are somehow related with quantum optics. I think it's one of the most strong quantum project, let's say, that is being established in Brazil. But I work in a center here in São Carlos. We have a lot of people, and of course, here comes the snake, right? And I have a big center, and it is financed by everybody that I think can have money and can give it to us. So we are a center from FAPESP. We are a national institute from CNPq and CAPS. And now we are a Embrap also project. And I put a phrase here because if we're going to discuss innovation, if we're going to discuss any type of entrepreneurship or things like this, it's nice to know that most of us in this place here, we do research. And this is a transformation of money into knowledge. But now we want to start to speak, especially in this field, on innovation, which is the transformation of knowledge into money. This means that, up to now, we are in one stream, and we want to reach the other stream. Innovation and generation of knowledge, they are not together in terms of way of being done. That's why I think, you were not in the same meeting I was in the morning when the minister said that we have to produce science that somehow transform faster in economy. I agree. And we have to do more and more science if you want to reach the level where we have enough to transform in economy, right? Because it's the word, right? Everywhere they do much more science, and then the opportunities appear. I'm going to explain a little bit how I see the innovation. Innovation, it is not stopping doing science. Innovation is stay in a state of alert to use science, and it's not for everybody. Because what we see today is a lot of people that are very much comfortable and used to transforming money in knowledge. But suddenly they want to transform knowledge in money. And that's not an easy transformation. It's not like making the Jacobian of this transformation. It's no unit, it's not one. It's not simple to do this transformation. You have to work a little harder here. Anyway, but because this is, I think, is a very qualified audience, let me say that we do work in many quantum stuff. Our center is focused in atomic physics, is focused in biophotonics and in nanoplasmonics, and all of them, they have something related to quantum, okay? And many laboratories I like to show because I think people is essential. We're not gonna do anything in any field without people. And this is true, right? Everybody knows. Anyway, we have many different experiments and related to quantum somehow. And this is the laboratory of Philippe that introduced me in a very vast way. And I understand that Philippe is very much interested in participate on this because he start experiments and theory in things like atom gravimeter, right? Which is something, is a challenge for us to be able to detect well gravity and to measure well these things. Measurement is always an important thing. And light scattering. So this is one of the proposals. And Philippe is also a laboratory involved with his collaborators that also belong to the center now, and they are almost all in the Federal University. And 2D light scattering, understanding all this process and localization of light. And atomic lighthouse. I think we can. I'm just mention a few things because I want to go fast to the other things, but I didn't want to lose the snake opportunity. And propagation of quantum correlation. I think this is a fundamental thing, and even the colloquium of yesterday of Cotter's lists, the colloquium of the people from Belém, you know, Costerlitz gave a nice colloquium yesterday, and he said many times about propagation of correlations and things like this, and interesting to understanding the fundamental. So this is some of the initiatives of Philippe, but quantum fluids is also quantum. It's a nice thing. We may not have a big application for now, but it is very important because eventually we can learn a lot about these many body systems. And in your laboratory, we have 3 condensates, and probably we're going to have a 4th one now. I saw Emmanuel, he's working in a dipolar type of condensate, and we've been studying disorder. Hughes Late studied disorder chaos in lasers for many decades in his life. Now we are studying in quantum fluids. And this is something very interesting because these things about out of equilibrium quantum system may be relevant for anything we do where we have more than a few quantum elements. And when you go to quantum fluids, everything is very nice because sometimes turbulence appears naturally. And this is something that belongs to the quantum fluids. You can generate a giant vortex. When it decays, it may evolve to turbulence without you want. If you want or not, it will evolve. So disorder may be part of those quantum systems when you take out of equilibrium, and that's something relevant. And recently we've been studying these non-thermal fixed points, which is when you take a quantum system out of equilibrium, is there any universality on this? And the answer is yes. There are classes of universality in those systems. And turbulence in quantum fluids is a very important universality class. And it's very interesting that everything scales, even though, you know, you may think that's a complete disorder, but it's not. The things evolve in time and in momentum space such that obeys some scaling laws. Okay. Well, this is another one in mixture because we want to understand many things, including the coherence of the quantum fluid. And matter wave. Matter wave may be also very important for coming future on quantum engineering. And we've been studying many analogies of what we can do with matter waves originate from condensates that people are doing very well with light already. And speckle is one of these things. We today can produce a speckle of matter wave. I think, in fact, we can produce the best speckle because naturally, when I produce a cloud of condensate, which is a superfluid, turbulent, that's a random combination of amplitude and phases that characterize well the evolution of the speckle or the speckle field. So we've been doing many experiments on this, and I put this in honor of Hussein, which is a very interesting professor that passed away last year. And he helped us to do a very nice correlation investigation in comparing speckle of electromagnetic field or light with speckle of matter waves. And we are able to produce a very nice understanding of this. Sorry, I'm passing very fast because there is no point on this. But what I want to say is many of the things that people has done with statistical optics, we can now do with matter waves. And matter waves, as you know, is very quantum and very interesting in terms of properties that can show. Okay, but we had a group here. Rafael is in the audience, and Rafael started an experiment with ions. Now he moves to ABC, University of ABC, and I hope he continues because I keep challenging Rafael to really produce the ions, and I hope he has something to report soon for us on this array of ions. And finally, we have the atomic clocks, which is one of the things related to quantum technology. Of course, an atomic clock is fully quantum, especially the way to detect. We have to preserve everything. We have to use methods that preserve the coherence of the superposition to be able to detect later. And we've been doing the fountain, and we've been doing the compact clock with very good precision. And if this is becoming even more important, and here I think there are possibilities, at least for our group, to contribute in a startup or even in addition to this nice project that you guys putting together, is trying to produce compact clocks because they will be necessary when we try to produce so many information per unit of time. Okay. Anyway, I'm not going to speak about the compact clock because I see time is passing too fast. But using quantum, you go in many things, including navigation, as you may know. And that's also another thing. We are using quantum mechanics every day, right? When we use the GPS. And this is became now not navigation just to indicate you, but to really navigate. You know, the vehicles fully navigate is already a reality, especially in agriculture. And then I believe this is part of a spin-off of this quantum initiative. We need a better quantum device for being able to really produce better vehicles that are classical, I know, but they are fully controlled by high precision that quantum clocks can give. And finally, the new system of unit. And I'm proud to, when this was established, I was part of IUPAP. And the new international system of unit is fully quantum. People believe that this transformation is a real democratization of the metric system. Everybody that knows well things, knows well how to measure, can define the quantum kilogram. And this is very interesting. And I think it's also part of thing because we need to be able to measure things on very high precision. I was telling Paulo before I start that if we are getting poor in standards, voltage standard is not any longer as used to be, is already based on the quantum Hall effect. And this is an important application because if we're doing aerospace, or if you're doing satellite, or if you're doing even aeronautics, which Brazil is an important player on this. This kind of standard is each time more important on society. And to say that we don't have a way to realize the quantum kilo, we do, but it's a very pedagogical. We have a small watt balance, right? We have the Gibble balance or watt balance that are able to realize the kilo using the principles, but of course in a precision very poor because we are not connected to the standards that measure the current and everything. Anyway, okay, so this was the snake part of my talk. I hope you didn't get too disappointed. But I had to say that, you know, we even have a lot of interest in this initiative. Now, let's start to talk about how we transform things in business, right? And there is a difference between innovation and entrepreneurship. And I think everybody knows because this is what we're discussing here, right? Innovation is what? And entrepreneurship is who? And you cannot do one without the other. Sometimes people are very innovative, but terrible business guys. They cannot visualize the way to put that in the market. We need both people. If we're gonna take any idea, any technology, and transform in something else, we need a guy that has vision and a guy that knows how to do. That's the difference. I don't know exactly what side I am. I think I'm more in the side of innovation. But you need the people that really can organize the things in their heads. Now, when I started to be involved with innovation, which is long ago, I put this diagram together. There are kind of versions of this diagram in a different way. And this is what is the obligation of each one? Research institutes, university, laboratories, and companies. Okay, so everything is aqui. Then here I have aqui. Paulo, my screen is a little cut. Is cut for you guys too?
Well, I see a full screen. The companies in the very bottom, I see companies. I don't know if it's cut. It doesn't.
It is innovation on the top.
Innovation scale up.
We can see that, and
I cannot see that. But anyway, maybe it's the format here, right? So, but you've seen the picture.
Yes.
Okay, look. Anything related to technology, anything related to startup, anything related to transformation of ideas in products, follow a common rule. And the rule is, everything starts with an idea. But the idea is not everything. It's a good point to start. You need it. You need 1 million of ideas because not all ideas are good. And then about 1,000, one of 1,000 of them are really ideas that can be proved in principle. A proof of principle is to give the soul for the idea, is give it the application. This is a proof of principle. So the idea is not wrong. It really can be used for. And then from those already dropped 1,000, you drop another 10 because you have to do a prototype. The prototype is the real application. You're not violating any principle. You're not violating anything. So pass the second stage. But then you have to prove that it's really good to application. But that doesn't mean that it's going to become a product. Many of those prototypes do not survive. Only a little bit will be prototype, will be product. Oh, sorry, from the prototype, only a little bit will be product. And from those, not everything works for the market. You know, there are too many initiatives for applicative of cellular. Not all of them make. In fact, most of them do not make. Because market means a lot of a requirement. And when we speaking about what we know how to do, which is consuming money to do things, we are in the first 2.5 stages. If you want to be in the other part, university is not good for this. Research institute is not good for this. You have to have companies involved. It's a different word. That's why I said research takes money. Innovation in the market generates money. Opposites. But you see, in the bottom scale, that is the value. What is the unity here? I don't care. You put the unit you want. The idea has a value of 1. It's not 0, it's 1. And the product that makes to the market, the idea that really makes to the market, has the value of 1 million. And who is the well-succeed guy in innovation? Is the guy that starts to put all the idea to reach products. What do you think? This is a waste of time and money. That's why Marcos, which I saw in the audience, which is now the coordinator of the Agência USP de Inovação, he knows that we should not patent everything. We should patent what we have a kind of idea or vision that will make it. University of São Paulo has 1.3 thousand patents, which generate less than 3 million reais for a university per year. This is nothing. So, if we want to play this business, we have to understand where we can go in one level and where somebody else has to take from the other level. And believe me, you need some people of vision. The guy that everybody wants is the guy that looks to the idea and already make this transit. You know, and those guys are the guys that make it. So the good exercise is prepare people of vision. That's why another day I asked Marcos, which is the coordinator of the agencia, which I was coordinator for 7 years. We have to prepare minds. When I said to him, what is the profile of entrepreneurial students we want? We want students that can really has a good vision. And I think today it's possible to start to prepare people that has this ability to be a visionary. You know, like the guy, I forgot the name, I'm getting older. The guy from Apple, Forbes, that guy was a visionary. Jobs. He was able to take an idea and visualize all this path. Really going on and starting things is better to stay in the domain that we are good on it. It's in domain of the first 3 stages. Because if we try to go further and we have no idea how to do, of course, I mean, always there is a chance, that we made the right choice. But this is like a wheel of fortune. You know, the wheel always win. Okay. So how institution that understood this is doing? Well, they are preparing special organized sectors of the institution, either an institute of research or a university. They prepare to give support for this. And that's like in the University of São Paulo is the Agência USP de Inovação, which is supposed to provide all the support for you to go in a soft way, the way that we have to go, and maybe help you the transition, help to find the transition. It's not easy, right? It's not so easy. So innovation, this is something I have to say because it's what I believe. For institutions like universities and research institutes, innovation initiatives do not replace excellence in science. I don't think it's by chance that Oxford, Stanford, MIT, and many others became a top innovative institution. If you take a look, you're going to see that they are also the top excellent institution. So it seems that they live together. But we do have a responsibility to produce leaders. We have to motivate more people to take the risk, to get abilities, because ability is something you get. Personality is something you have. When you match abilities with personality, is the success. So I believe that we as universities or research institution we don't have the bank, so we gotta produce leaders. And we have to be in state of alert. Everybody always come across in any type of research, from mathematics to linguistic. Everybody comes across opportunities. And the problem is, we are not training to be alert for the applicability. We are alert for getting a good idea, put in the paper, publish, because we are paid for that. We are training for producing more knowledge. But now, in the modern world, even good scientists in basic science has to develop an extra sense of being in a state of alert to be able to indicate. He doesn't need to do it. Nobody's asking anybody to start a company, but we are asking good scientists to indicate promising knowledge that can be transformed in important technology and can go on. We have to be opportunity facilitators. You know, that's what I have been part of my life now. Try to viabilize that people that we can identify as fulfilling a few requirements can actually go on. And I think we've been doing well with this in optics. As I said to you, I have no experience with quantum in the business. In any way, we are not business office. We are not business office. You know, and I offer myself to invite Chris Monroe one day to speak to us because he gave a wonderful talk on the National Academy of Science in the United States. And basically he said, there is a transition. University and business. Even though the American institutions, they have a good sector that do business because they live out of business. The scientists is not the one that are doing. Okay, now, as you realize, the entrepreneurship or the guy with this spirit of entrepreneur is the main element. And what is this? I mean, you know the definition. I'm sure that you guys been reading a lot about this. But, you know, one of our responsibility is foster the culture of entrepreneurship through different initiatives. And I know that I have colleagues here in São Carlos that sometimes say, why give a colloquium about this? Because, you know, we have 200 students in the colloquium, but maybe 5 of them are the ones that are going to keep these institutions going on in the future. So we have to create this habitat of innovation, even though not all of us do innovation. But we need to create, because a few will carry the boat or the train away and keep us running, because we need to keep running. Scientist is like, you know, utopia. How you say that in English? Utopia, right? Science is like utopia. You never reach the final. You always approach it, because the final of advancing knowledge, it doesn't exist, right? So we are, you know, that's why utopia is used for, is to keep people going in one direction. And we are good on this. Scientists is good on this. But for startups, for company, for business, you cannot be utopic. You have to be more precise, because society are available to pay us to advance knowledge, but not to keep your business without success. Well, I think motivate and well-educated students can think about starting business. We can help. Now, I put something here that I believe are important stages when you speak about startup. First stage, I don't know if I quote this word in English correct, is ideation. Is that a word, Paulo? Ideation? Maybe no, right? Idealization, maybe. Well, it's missing a letter maybe there. Anyway, as I said from my scale, things has to start with ideas. You know, if you really want to be innovative, you have to start with the idea. And the idea is the seed. But if you don't put the other nutrient, if you take a seed of orange and leave it on the table, it stays seed forever. You need something else for that to germinate and produce a tree and produce fruits and live by itself. That's why I think it's a good example. Second stage, people have to worry about making the things, formation. You have to go beyond the verification of possible legal limitations and everything. So if you're going to have a startup, there are some things you have to worry about. And you have to start to have an idea if that's going to be a product. There are clients for that product. I had many ideas that did not survive for this stage. because there is no client. Nobody wants to buy everything. You know, have to be very careful what you think in the second stage. The third stage is traction or creation. This is where the entrepreneur plans the solutions, where to put the ideas on the table to create the organization of this startup. Fourth step is the validation. Well, the validation stage is really the opportunity that you can see what you're doing work for. And finally, scale and operation. Because you cannot have a startup to stop in what I can do in my lab as a research. Startup, they have to do research and the next step. Well, we have some experience here with startups. All the companies in optics in Brazil, they did not, in São Carlos, I'm sorry, they did not come from outside. They were born here. And most of them born from our lab, along decades. Today, I could count about 46. But you see, there are many that transform themselves, and I do not consider as original as was before. But if I consider the ones that moved to another thing, I could add another 15 here. And they have... our group helps more than, this is not the companies, this is partnership of our group. We help to launch more than 7 products in the market. How many of them are good success? Boy, I don't have that statistic, but I know that they all produce, they all went to the market for a while, and most of them are still today. Still today, they are there. And some of them is being launching now. I put here on the top left is the synthetic curcumin that we just end producing and a company start. Because the curcumin is using for many, many things. It's a molecule, it's quantum too, but we don't consider it like the part of this synthesized molecules, more on the organic chemistry, and they start. But there are many things here that use many things that you all know. Okay, well, one thing that I found, and I talk a lot with my friend Jarbas Castro, which was one of the pioneers on this, is you have to make companies, and when you make a lot of them, it's nice if they talk each other. We realize that sometimes companies are consortium of companies, startups or not startups, is the best for surviving. They always are being able to be the provider one for the other. Instead of competing, they help each other. So they all go together. And I see this in many of those companies I see here. Okay. Now, there is a wrong cycle on startups. And let's say that the idea is good. So idea is good. You know, it's good. We discuss in the table. We pass those stages. It's good. The company can only spend its efforts and resource with the advance of the idea. PP phase 1 of FAPESP. You have a startup and FAPESP gives the money for the company to prove the idea. Well, company, this is a first stage, but then you have to go on, right? Comes the PP2. But sometimes the company cannot go on. They do another PP1. And they keep doing PP. So those are the companies that never going to have products in the market. There are many, many of them. They always work with the idea. They will be better off being research groups in some institution. Well, this is not what you want. But that's a big risk for the quantum technology. Because, you know, we hear about quantum computer and everything, but today I receive, you know, in those flashes that comes in the computer from physics world, that now they are making the first devices with the room temperature superconductor. I think this is big. because we're speaking about high TC superconductor as a big breakthrough of technology. But so far we didn't have anything. It seems that 2020 has a bad news of the COVID, but has a good news. Maybe we're gonna have devices, superconductor devices at the room temperature. With the quantum computer, I see, you know, I went to see the round table in the National Academy of Science. That Google was there, Chris Monroe, IBM. That was 2 years ago, but I see that they're still in that stage. I know that quantum communication or decodification and everything is even, you know, information in general is closer to reality than the quantum computer. But we are in a stage that we're still working out the ideas. We still do not know all the ideas that will be products, but we already speaking about startup. Okay, but is that a mistake? No, I don't think so. Because this is so dynamic, the dynamic is so fast. You know, the things is so speed up that I saw the guy speaking in the morning. He was making a kind of timeline on the events and everything. That things are going so fast. If we don't do kinds of startup, we may be too behind. It's like making the active principle of a medication, but not being able to put that anywhere. We don't want to be in that stage again. So I think in the case of quantum technology, we have to think about startup in a different way. You know, the German people are very good for that. You know, Fraunhofer is a big success in transforming knowledge in technology. And I think one of the things, they don't do all in that way. They do many things. They can have contractors and a big company can go there and say, solve my problem. They do and everything. But there is a concept that is what I call the translational projects. Are projects that are within the Institute of Research, are within the laboratories, but they have the aim, they have the goal to transforming products or to test that to be product. So they are with us. We are helping because they are proving ideas, they are proving capability and everything. And we can let the investors, because we need money, right? To watch that. They can observe. And then there are feedbacks. Many projects will just continue to be good advances of science, of knowledge. But some of them will evolve. Some of them will pass to some proof of principles and will become a startup. Opa, that is a mistake, but that's, you don't care. Some of the ideas may come to this. I know that's hard to get money for this, but people are already paying attention. Because if you're going to start a startup, they don't have money. They need the support. For doing this translation is a group of people that already wants to be a company. But they are not prepared yet. They're going to be officially a company with what we call a juridic person. When they prove it, they see the first light that can be going to the market. Well, like suppose you have a PIP, one of those projects of small companies in the FAPESP. That should be in a lab. So you finance that. And if that's evolved well, you go to the next phase. And the next phase, it can go to an incubator. You can go to a park, technological park, and so on, and keep going. If not, we can try another ideas with a group of people. Or even they may decide to do something else. Now, Embrap is starting a special program of startups. And the idea is to do exactly what I told you. They give you up to 200,000 reais. We're not sure exactly the amount. we apply for this, but I think we're gonna come only the second round because I am already Embrap unit, but I'm proposed to the Embrap in Brasília, which is the Empresa Brasileira de Pesquisa e Inovação Industrial, to allow me to take 1 million reais from the money I have to try myself, even though informally I'm doing this. I have 3 small group of people that want to be companies, and they are using part of the lab for doing this. And the university has to adapt themselves for this. Because you cannot request, imagine in the field of quantum computation, what are you gonna ask the startup to have? What kind of hardware? What kind of infrastructure? Or we are talking about startup only in the software business. Then maybe they need a computer or something. More theoretical. Yeah.
You have 5 more minutes.
5 more minutes. Oh, I'm finishing, Philip. Thank you. Anyway, this is a project, and this is a startup cycle 2. Is when the idea is already very well solidified. It's not yet a product, but has to be prototype, has to be proven and many things. And I think Embrap is able to do this. And I think I want to reserve some money for being part of this initiative, embracing some startup that can try the idea, but under the arms of a good research institute, where they can try, they can discuss, and they can take decisions, go on or retract. Well, Philip, thanks to you, I finish. Guys, well, message to take home. I think, this is a good opportunity because the whole world is going for this. And we should have initiatives. It should be together with the research institutions. I don't think dropping those companies in incubators right away will, because I see nobody to buy that immediately. It will be much better to have efforts to invite the investors, angels or big investors. I saw a talk another day that even Google are looking for startups in this business. That's investors. They can come observe financing, and then they decide, go on or retract or quit. If they quit, we have a collection of good people to go on with another idea and so on. We're not going to spoil people or ideas. Anyway, thank you very much for the opportunity. Paulo Vilas Boas, I think, I don't remember who I received the email, but it's a pleasure for me to speak with you guys. And I think this initiative is really important, and you should go on with. You see, we're never gonna lose. At the worst, we're gonna produce even better science, and I think this is the wonderful project. If we never lose, we always win. So let's go for it. Thank you very much.
Thank you very much, Vanderlei. Thank you for your interesting insights on quantum mechanics. One of the goals of this initiative is, of course, to educate people about what quantum mechanics really is, in order to avoid misunderstandings of the kind that you showed on your first slide. No? So this is very important to educate people. It's a precondition to make quantum technology a reality in São Carlos, in São Paulo, state of São Paulo. Okay, now comes the part of the questions. No? Are there any questions around? No chat?
I have one. To Rafael, I want to know how is the ion trap?
Yes, Vanderlei, I can answer so much. So I tried a lot. That was.
How are you, Rafael?
I'm fine, thank you very much. So in the beginning, when I went to ABC, and that's really a good reason that these quantum technologies may help me a lot, is that when I tried to apply for PESP money, they said that I wasn't qualified enough. So I hadn't spent so many times in the outside, and I haven't had a really good background for them. So unfortunately, I couldn't have any money to build an experiment. So, and then right now, what I'm trying to do is just to upgrade my CV. That's why I'm in Denmark right now, doing another postdoc.
Okay. Yes. It looks like a ABC, but fine.
Yes, yes. It's a little bit colder, and a little bit darker, but yes.
Okay.
But thank you very much for asking. Yes,
and I know it's hard.
Yes, it's very hard, yes.
I see so many young people that are having difficulties like this. And maybe one of the jobs of the people that are getting more senior is to show that we have to risk more. We have to be more aggressive than we being. You know, every time that we approve good things that as is very well known, that doesn't take anything up. That just keep the car moving without direction.
Yes. Yes, thank you very much for asking.
Raphael, we have been talking to Rainer Blatt. He's willing to be part of the advisory board of this initiative. And of course, he's always asking about the progress of the Iron Trap experiment.
Yes, before coming here, I was writing a project and then I got in contact with him. So, but thank you, Philip. Yes.
Yeah, he's very interested in seeing quantum computation become a reality in Brazil also. No?
Yes.
So he's yeah.
Felipe, tell me something. Is there any startup on this quantum business already?
Not as I know, in the state of São Paulo, not yet. So,
Felipe, yes, there is, right? And it's one of our supporters that we talked to in the beginning on the software side.
Exactly, at São Carlos.
In São Carlos.
But I believe Marcelo Martinelli and Marcelo França Santos, the bosons, want to make questions. So please, Philip.
Where?
They have raised hands. So Marcelo Martinelli first.
Paulo, can you put us in the screen as a all? We are in the very corner here. I cannot see anybody.
You actually
I have to do that.
Yeah,
you can stop sharing your screen. Yes.
Oh, yeah. I did, I think.
Nope.
Oh, no, I did not. So, thank you very much. Now you can see a better panorama.
So what do I have to do here?
Marcelo Martinelli.
Which one?
Can ask. Marcelo Martinelli can ask the question.
Okay. Vanderlei, comes a curious point in my mind when you said about the distinction between innovation and entrepreneurship, and innovation as a matter of what to do, and entrepreneur as the one who will know how to do. And then they mentioned a certain dichotomy between vision and knowing how to do. From the models that you have seen, should they be different people or different departments, or that should be? I would like you to comment a little bit. Should there be a partnership between those who can innovate and those who know the market and how to introduce a product?
Well, I gave you the concept. I didn't say that one person cannot be both.
Oh.
There are many, many initiatives that a single guy is both. He's able to develop an innovation, and he's able to manage.
Sorry, I just.
What? Marcelo, you have a. I
have a crappy connection. It cut. I don't know if you went to the end of my phrase, and I lost completely your phrase.
Okay. What I said is, I gave you the concept. And I didn't say that a single person cannot be both. There are many, many examples of a single person that are make the innovation, organize the innovation, and organize the way that this innovation is going on. So he's already, of course, to be innovative, you have to be a little bit entrepreneur. But the entrepreneur is not necessarily the guy, is the guy that are able to take a good idea and transform in product. This is a good entrepreneur. And normally you want the two things together. And sometimes you don't have it. You have a combination of people that have different abilities. One is very good in innovate. One is very good in producing the innovation. And the other one is very good to make up the plan, how that is going to go on, how that is going to be transformed in product or in something else. Or sometimes people are even so good that they get the idea, even if the idea is not great. A good entrepreneur, he makes an idea. An entrepreneur, even if there is no market for his products, he creates the market. He creates the desire in the person to have that. You know, the guy Jobs is one of those guys. I mean, you know, if you ask me 30 years ago, do you want to do banking in your cellular phone? I will say, what? I want to see my manager. I want to see the guy. I want to discuss with him. But today, it's different, right? And they made us like that.
Thank you.
Now, I don't know if I answer. I hope I answer your question, Marcel.
Yes, you did.
Vanderlei, the examples of the startup companies that you've given, they are all triggered by results of experimental research. So it's a kind of a bottom-up initiative. No? Now, if you compare to the quantum technology initiative of other countries like United States or Australia, Europe, there's a master plan. There's some governmental institution who tries to make a master plan, and so it's more like a top-bottom initiative. No? How do you see the possibilities of implementing such an initiative here in São Paulo?
Well, see, we are a different culture, right? In the United States, I think the leadership knows what they want. You know, I always find that United States, they know we needed to have the bus driver, but we needed to have a happy bus driver, not any bus driver. So they invest on that. They make what you say a plan because they want to make the whole thing to grow. You know, to put the man in the moon, the government made a full program of opinion and start museums, start everything to make all the young people like fascinated for that idea. And well, we don't. But you know, Philip, our country is being developed in a different way, I think. But it's much better than it used to be. You know, it's much better. I think now the universities are very worried about transforming knowledge, but we don't have a master plan, as you said. We don't have a kind of architecture that can, you know, take the pieces. They know everything they need. You know, I remember when I was a young kid, is when Senai start. Because before we had companies, but we didn't prepare the technicians. How are you going to have automobile companies without having people that learn in school how to deal with the machinery, the lathe and the you know, the wheeling machine and everything? So we need a kind of thing like this. If we want to make technology to push, we need that. Embrapa, in some sense, made a small scale of that. They knew what they needed to do for agriculture. So they know that they have to talk from the tiny little producer, the guy that has 100 by 100 meters, until the big producer, the guy that has a latifund, a big piece of land. And they knew that they should worry about technology for both ends. And you know, Brazil is being sustained by agriculture. And I think we need a master plan like this. But as I told you, I'm not an expert on this. And we don't have a lot of experts. You know, I think the initiatives we're having, and I know the University of São Paulo, and some incubators, some parks of technology around. and the condominiums of companies. You know, here in São Carlos, we start what we call companies fraternity because there was no enough incubators. We start a kind of a república. People that speak Portuguese know what it is. República. We help the guys to rent a house, and there was 3 companies there. And because there was now, you know, University of São Paulo is organizing, and many others around the country, not only University of São Paulo, Unicamp is even very advanced on these concepts. And people are organizing the environment and everything. You know, took us how many decades to really have the first technological park connected to the University of São Paulo. Now we have not only one, more. And incubators, how many, you know, now we have. São Paulo is an example of a good success with the incubator. So now we are starting to organize. And then I think we're going to produce enough people thinking that they can make, when they became leaders, they will make a master plan. But we cannot wait, right? I remember, you guys too young, but I remember the semiconductor program.
Yeah.
Brito Cruz is here. Hello, Brito.
Hello, Vanderlei. How are you? Good to hear your talk.
Well, nice to see you. Yeah, but everything is evolution. As I said, we are much better than we used to, but we still have a nice road to go. But we cannot stop, right? We have to keep going.
We have another question. Felipe. Marcelo Santos just lowered his hand. So Felipe Barbosa.
Hello, hi Vanderlei. Thank you for the talk. It's very nice. I just wanted to ask something that maybe you already touched upon it. It was the people who are here in the morning. They talk about state-based funding for the companies, their companies. But especially Mian, he talks a lot about venture capitalist funding as well, funding from the private sector. How do you think this compares in Brazil? How do you think that is the private sector here they are willing and they have the resources to invest in this kind of new technologies?
Well, look, I've seen many initiatives with the resources for financing projects of high risk, in fact. And, there are even BNDES, even the National Bank has a kind of fund for financing projects. I don't know if in this kind of a startup, I think we have a basic FAPESP. Now we have maybe this Embrapa allowing the units to start some startup. But I'm going to do if it is like the way I told you, right? Translational inside the lab for a period and then they go out. And but there are, I don't follow very close all the things. But recently I received a few emails of representative of angel investors that are interested in finding good projects that are of high risk in very high technologies to put money. I think if you have a good product or a good idea that you go for product, and you have a good interlocutor, I don't know how to say that, a spoken man that are able to sell well that idea, you can find people that will finance. There are many resources around. I think Brito, he knows better than I because he is involved in seeing startup companies from PP projects to go for those monies around. I don't know, Brito, you want to add something here?
No, Vanderlei, nothing to add.
Sebrae for a while was financing, but his financing, I never saw Sebrae really coming with ultra high tech project. They normally financing small business and things to keep going, but it seems now they prepare something and they are being connected with the Minister of Health and Minister of Science for specific projects. But I cannot say too much about because I don't know. Marcos.
May I say something?
Just a moment, please. Vanderlei, because it's about Embrapi and you were talking about it now. We received the question from YouTube. Natalia Tomasio sent it, and she thank you for the talk. And Vanderlei, you mentioned Embrapi. What's the eligibility criteria to get funding from them? Do they fund research projects or only projects linked to startup company initiatives?
No, Embrapi is the following. The mechanism is a little different. They select places that are the unities, like we are a unit of Embrapi. And then I make a work plan. So I say, for the next 5 years, I need 10 million. And then the companies, either startup, any company can come and say, look, I have this project that I want to develop with you. Embrapi is for partnership. Embrapi pays half of the research in money. In fact, it pays 1/3, but 1/3 is just the infrastructure and everything. So it's not financial. It's not money. It's just the infrastructure. The counterpart that we give is the use of the infrastructure. The company comes with half, and Embrapi comes with half. And the company has to look for a unit. So if this company comes to my unit and with a decent project, then we make a working plan. I have people, I organize a group of people that takes care of this. And then we approve here. Once we approve, it goes, we sign a contract and we start the project. And Brasília just endorse if it is within the scope of abilities that I declare in my units to have. So it's a different thing. It's not like the PP, the program of FAPESP that give the money to the company. The Embrapi gives the money to the unit, and the unit shares the money with company developing a project, which has to be developed in partnership.
Okay,
Marcos.
Thank you. So now it's a good moment for Marcos.
Yes, thank you. I wanted to make a comment on Felipe's question. I think that venture capital in Brazil is growing fast, and it's growing strongly. And we have a lot of angel capitals, because when the startups are just beginning, it's called angel capital that give money to them. And a later stage that the venture capital enters. And it's growing very fast, I think, because of two factors. One, because there's a lot of interest in our startups in general. And the second reason is probably because of the low interest rates we have now in Brazil. So money is cheap, and people are looking for other ways of making investment. So I don't know if that will last much longer, but now we are in a very good tide for this kind of investment.
Thank you, Marcos. Can we hear Brito now and then Vanderlei? The silence is a yes. Go, Brito.
Yeah. Yeah. No, I was going to say something very similar to what Marcos just said, which is for the type of initiative that you are preparing, it seems to me that it is the path of funding for a startup would start with angel or with FAPESP, small business, the PIP, or if you are in one of the Embrapi units, then you might be able to use as Vanderlei described it. But those are much more restricted. And having a unit at Embrapi depends on them announcing a call for certain topics and this and that. So the units which exist. Nobody knows when they are going to open new calls. But anyway, that would be useful. But you might start with angel funding, which is private funding from whoever, or with PIP. And then the challenge will be to obtain venture capital to move to the next steps, because the thing that happens in the United States is that when they move to venture capital, they increase the scale of the operation of the startup by a factor of 10 or 50, depending on the level of VC. So usually it's a researcher who works in a university and uses $1 million per year. Then they get an angel funding that gives them $500,000 for the first 2 years. And then they get $10 million from the VC. So the number of people working, which is what makes a company grow, increases a lot when you get to the venture capital stage. And as Marcos was saying, venture capital is increasing in Brazil because the decrease in the interest rates of the central bank is forcing people who have money to look for honest ways to make more money. So they have to get into some kind of risk with their money, not just lending it to the government and getting whatever 3%, 4% by the end of the year. So there might be opportunities, but in the case of quantum technologies, I would try to think about not building a whole machine like the IonQ startup from 2010 and other companies, but looking for small opportunities related to certain parts of the quantum computing. Which one is the thing that, with what you guys know, you could do better than anyone could do in California, because you have that first step that Vanderlei mentioned, which is an idea for solving one of the bottlenecks in the big IonQ machine or whatever, the Canadian or the Cambridge Quantum or whatever. So it would be a good thing to study those machines and look for the bottlenecks there. And not only bottlenecks, but bottlenecks in which there would be a sizable market for the thing. That would be the kind of thing that PPFAPES would love to receive. Thank you.
Yeah, I agree, Brito. You have to do what you think you are good on it, right?
So let me jump in.
Combining this necessity with opportunity. You have to be, where are the necessities, and combine with the opportunity. Anyway, Brito, it's always nice to see you speaking.
Let me jump in with one first observation, which is, I think Brito's question or comment moved us directly into the brainstorming session. So I would like, to make it official that we're in the brainstorming session and have people really consider not just Vanderlei's talk, for which we should again thank him, but also consider the whole initiative and the way we have to move forward. I would like to make one comment on startups. Vanderlei said that he didn't really know the rate of success in these startups. Call the attention that even unsuccessful startups, if they exist for a while, they're already economically beneficial to the state, to the country, because they're already paying taxes and they're employing people. So while they exist, they are already beneficial. And the usual environment of startups is like that. A lot of them are created, there's a big wave, Not many of them will actually survive for very long, but that doesn't mean the initiative was not successful. So this is one point. The other point, which Brito mentioned about capital, venture capital, this morning, Mian made a comment about venture capital in the company in the US, where they were able to get away without venture capital so far, and that eventually they didn't want to move at this stage to, massive production. I'm sure, I'm glad to see Nicolas already raised his hand, so I'm sure he's going to comment a little bit on the French side and their experience. The other point is, I definitely agree 100% with Brito that we should not begin this initiative aiming at full-scale, complete, integrated systems for doing, quantum computing or whatever other task. We should focus on smaller things that are achievable in the near midterm future. And this is what's going to establish an environment that will further other initiatives and that will help us go forward. So I definitely agree with that. And I think this is something that we want this community to really help shape the initiative in that sense, to help us bring up for the roadmap the kinds of ideas that we can envision that can generate revenue, that can solve problems that are going to be competitive internationally because they're going to be devoted to local issues and nobody's going to come solve them for us. So these are the kinds of things that I think we should have in mind. And maybe Nicolas can jump in now.
Yeah, I just wanted to comment on your first point, Paolo. I fully agree about taking a risk. And I think, in fact, it's a problem we have both in France and in Brazil. And from what I see, the US do much better. So they have much more startups that do fail. And I think this is important. If we don't have enough startups that fail, it means we don't take enough risk. And what they say usually is that if 10% of the startups are a big success, it's good enough. This is what you are looking for. And we are the same in the French system. I know barely of any startups that have failed. So there's many which are surviving, which is good, but it means we are not taking enough risk. So we should have incitations for people to try. And trying a startup for 1 year, even if it fails after 1 year, it's a good thing. It's a good experiment for the people that do. It also teach people something, so it's a useful thing for the country. So we should not fear about failure of startups. I wanted to insist on that. Mm-hmm.
The floor is open. Maybe I could actually invite, for instance, I'm not sure Harry Westphal could say a word about the different companies that helped building the Sirius. Eventually, we feel that some of these companies could actually contribute or be interested in developing quantum technologies. So maybe, Harry, if you could make a comment on that.
Yes, thank you, Paul. Can you hear me well?
Yes, very well.
Okay. Yes, definitely. We had the participation of different companies in different aspects of the project. For sure, those involved with low noise electronics, vacuum components, cryogenics, and X-ray detectors. These are the ones that perhaps could be involved in this kind of an initiative, and they will surely benefit and make profit of this knowledge. I think one thing that most of these companies profited the most from the interactions they had with the Sirius project, from what I saw, not only that allowed them to grow, but also the kind of knowledge that they acquired along the project that would not otherwise be transparent just for being in the literature. I think the contact that they had with the researchers and the engineers that developed the project and transfer this kind of knowledge for them. And I think this was the major profit. So it's the kind of knowledge that you guys have, and that's what they think that they seek the most typically in this kind of interaction. Obviously, they have to have profit and they have to produce a product, but the kind of knowledge that you developed in universities is not part of their daily lives. I can see for many examples like X-ray detectors that were developed for the project. The company that developed this with us, they never heard about an X-ray detector before they started working with us. But they had a very strong base on high-speed electronics and telecommunications and aspects of this detector that were crucial for the project, and we didn't have. So this is a kind of example that after they developed with us several components that were crucial, like flexible circuit boards that were kind of standards in the microelectronics industry, but were not part of the Brazilian technology, let's say. So they could develop by themselves for this project, and then they could apply this technology in other areas completely unrelated to X-ray detector. Or even the VAG company that developed the magnets for the synchrotron. They also, they learned several aspects of control and high current density that they had to apply to the magnets that were not part of their daily lives. And it's the kind of knowledge that they wouldn't otherwise acquire if it was not for the project that they got involved with. So I think several of these companies would certainly benefit, and more companies that if you search, I think that the hot spot is when you find something that they can increase the knowledge of the application that they are doing, even if it's not related to, let's say, quantum computing, quantum information. But the side products of this knowledge transfer would be quite beneficial for them.
So in a sense, you are reminding us that we had a very good example of a top-to-bottom case where even companies that were not even aware of what to do decided to do because someone made the master plan and said, okay, we will have synchrotron radiation here.
Yeah.
Thank
you.
I
think, yeah, that's right. So.
There was one question that we missed in the morning part because it was more related to this brainstorming, and then it disappeared, but I believe Cauê put it in the YouTube. That's about interactions with the other states in Brazil. So if someone wants to comment more about this, if no one else, I will. Okay, silence, so I will. So one of the important parts that we decide to do it at São Paulo because FAPESP can do the thing, can really make this master plan available. But we really believe that it's only the really seed situation, that the major part of the money will not come from FAPESP. And of course, FAPESP money is related to São Paulo state, but any other money does not care about boundaries, frontiers, whatever. So we really believe that it will be a national and in some case even transnational thing that we only started here. So everyone from other states are very welcome to participate. And of course, we really want to make it, the technological part has to be related with entrepreneurship and etc. And all of this is really open, and we do want help in the beginning and collaboration during all the time with everyone else.
Brito wants to say something.
Yeah, I'm not sure if the discussion today is only geared towards innovation and startups, or if I could say something about the idea of the program in general.
That's more than welcome. That's actually what we want. The brainstorming session is about the next steps that we will take. Of course, we already thought a lot about that and we've planned, but it's really important to bring this community together and to have people hop on board. So
okay,
please.
So because I find this initiative very, very interesting and very good, I will share with you the things that I used to consider when I was at FAPESP, when people came to me with the idea for a program, right? So that I don't know if they are still thinking the same way, but I mean, the institution has a way of thinking about things. So you might want to consider that. One of the things is that the main argument for creating a program is, in my view, was not really about a promise to create companies or business or helping industry. The main argument was always that they had a convincing argument about making better science if they would work as a group, as a connected group of people, as opposed to working each one in their own things. So that's it. It's the thing that I use it to call, like, you have to demonstrate to me that 1 + 1 is going to be bigger than 2. That because you are working together in a program, in a connected way, with an advisory board, with meetings and with some structure and whatever, in 3 years, we are going to see reasonably better science in this field in the state of São Paulo than we have today. Because that's what would make the foundation pay attention to it, right? Because otherwise they can just say, okay, go home, do your stuff, send your thematicals or whatever, and good luck. So 1 + 1 has to be arguably more than 2. The more it is, the better. So you have to build an argument around that. In this case of quantum technology, another element that I am almost sure they are going to ask at some point, if they don't, the reviewers, the international reviewers, is the size of the community that works with that in the state of São Paulo is a size that competes in the world. I don't think it is. So part of the reason for a program might be to increase the community in a qualified way. So, for example, when they came to me with the bioenergy thing in 2007, I spent almost a year trying to convince them that they had to promise that they would bring 5 young investigators every year to increase the size of the qualified community, to have more labs, more ideas, more people, whatever. So young investigators who can be Brazilian or can be non-Brazilian. They don't have to be Brazilian, but bringing those people here to make the community stronger. And the other thing about building a community is using another program that FAPESP has, which is called the São Paulo Excellence Chairs, through which you can bring a very experienced researcher for 12 weeks per year, for 5 years. If the person comes here 12 weeks per year for 5 years, they can have a thematic grant of their own. It's not, you don't have to have a laranja to take care of the thematic. It belongs to that investigator. It's in their name and so on. So increasing the community, forming students, having more postdocs, and bringing young investigators. So now, if you have those two things, then creating startups is a desirable thing, but it's not the main thing. I mean, I don't think anyone at FAPESP thinks that we are going to make a business out of quantum computing in the state of São Paulo in the next 5 years. But if you show them that you might create some small companies that will have ideas and so on, that would be okay. But the chance that those companies are going to be competitive increases as you demonstrate that you are going to have really better science in the next years, because those companies will come from the ideas, will come from the science. So those would be my 5 cents at this point.
Anybody want to hop in?
No, actually, I have one question or comment, or actually, yeah, question to Vanderlei, connected to the one that connected to what Brito just said. The question is, so out of all the aspects that you mentioned regarding creation of startups and so on, if you had to pinpoint one that you consider it to be the most urgent for us to tackle here in Brazil, like this is the one that like we should tackle first. This is the thing that is creating more difficulty for us. And is it the same thing that happens abroad, or our difficulties are different from the ones that people have in other places, in your opinion?
For Vanderlei.
Oh. Well, you see, in this field of the quantum technology, I don't have enough.
In general, Vanderlei, in general, startups in general.
Oh, in general.
Quantum technologies, yes, in general. Like, in your opinion, which is if you had to pinpoint the most urgent thing that we needed to tackle in Brazil, which is the biggest stone on our way, which is the thing that we should remove?
Well, see, what I've been realizing in well-succeed startups is that, well, first of all, they always rely on a good idea, but sometimes they are not prepared to be products. And I agree what was said. We don't have to have success in startup in the, all of them. We need a fraction of them. And what I realize is that the ones that work in necessities, they have good opportunity for success. So I see the startups with good ideas that really fulfill some necessities of the market. They grow very fast, because otherwise the track is very long for them to make there. Now, what I should say for the Brazilian startup, we have enough well-succeeded startups. The problem is I've been seeing startups that are 10 years old, and they have survived with a series of projects, and sometimes even moving to different projects because some of them did not work. So I don't know, to answer your question, I think we have, well, first of all, we have to have enough startups. And I think is missing the money for the startups. We need to have a more aggressive program of startups. We have, we always mention 2 or 3 options, but, PIP, Sebrae doesn't do anything for startup, as far as I know. FINEP doesn't do good for startup. BNDES had the one startup program. I don't know how was that. Maybe Brito knows. So we need more initiatives. I think PIP is the best well-succeeded program for a startup. And they have good examples. Now, what should we do is intensify. And of course, point out the directions for a startup is a good thing too. So now we have problems with, we've seen that suddenly we don't have enough infrastructure, not even to make masks for hospitals. I mean, you see, this is a situation that's bad. But a necessity always is a good start for a good success with startups.
Thanks.
Hi, Paul. I would like to make some comments. I think I see this problem, or maybe like a very important role that these projects might have, is that I think we need to build, I think, a bridge with engineering, basically. I think we need more engineering to do better science. I think many of the groups, I mean, I want to enter in the quantum networks business, and I follow the works of many groups in São Paulo as well. And we all need to develop better technology to do better science, I would say. And I think this field of quantum information is really fortunate, I would say, to do this. I mean, because we have this common language which is quantum technology. We can talk with engineers, we can talk with computer scientists, talking about problems that interest them, but we can also do more interesting science, more important science with this know-how. And I think you already comment on that in the morning session. I don't think the physicist has the know-how to do everything that's necessary in the field. And to build these bridges, I think it would be really nice to have like a large project that you can really create larger challenges that would involve engineers and physicists working together, because it's really, I think it's important to work, I mean, in the background of physicists, the background of engineers, I mean, at school, at universities, or maybe start to form different kind of professionals that are in between the fields. But I think this initiative would be really important to really bring these new people on board, but with common challenges, I would say. Because I mean, I think the field of quantum information has a lot to offer for information science, for electronics, engineering, for many different technological fields, and we need them. I think that's the way I see it. I mean, this large problem.
Thank you, Daniel. We agree 100%. Even Pierre-Louis already said that he agrees a lot and gave the example in Clio. But let me include, and we are making this effort, and we want help of all the community to make the same effort to announce it for people in engineering, computer science, and wherever, that we really want it to be larger than the physicist community. But let me make another comment almost in the opposite way, but also opening possibilities. You experimentalists are very used to instrumentation, but usually you do it in a kind of amateur strategy. You do a fantastic instrumentation for making your own experiments. And in many cases, it's just one step more to make these instrumentation talents to become startups and to enter in the innovation part. So that's something that I think you should have in mind. That's really something that you are very close to cross another bridge. And the larger the number of bridges that we make, the best connected will be.
But actually, that's exactly what I'm talking about. I think, I mean, in physics, we don't learn anything. We don't form students with the tools that we need. I mean, we need a lot of control technology. We need a lot of digital, I mean, technology. And the students in other fields, they are formed. They end up the course already with the basic knowledge on that. So you really need to cross this gap. So I already went to some of my engineering department here in my university to give a talk and talking about some of the things that Paulo talked in the morning about quantum supremacy and the way things are moving towards, but also actually enlisting the challenge of my lab. I mean, that I have many challenges that I need really more support to develop something from there. Because I mean, if we want to scale up, I don't think we were going to scale up with physicists. That's the point. You really need to do a different kind of planning of the experimental setups. You really need to I mean, we would do that because I mean, we are motivated, but it would be much faster with engineers, I think, on board. And I think they will enjoy it. That's the point. I think we have a lot to share.
Let me jump in again. I wanted to make two comments. First, the fast one, Igor wrote in the chat that he has practical questions about spreading the information about the initiative to a broader public, if we have a press release or something like that. This is a kickoff meeting. So we have been working on this for 3 months. But we're far from having something ready to submit to the general governance of FAPESP and to launch a program. So obviously, once a program is launched, there should be press releases and all that. On the other hand, there's no secret to what we're doing. So definitely, you know, anybody who is interested, and especially those who would like to contribute, information is free to share. This whole meeting will be available on YouTube. So again, absolutely free to share. Now I want to come back a little bit because it is such a privilege to have here with us somebody who used to evaluate whether programs should go ahead or not. So I want to come back to what Brito was saying. And in a certain sense, I think what we have in mind or what we're coming to is probably not the regular, the usual program that FAPESP has made so far. We have a community in quantum information, quantum science community in Brazil that showed exactly what Brito mentioned. Bringing the people together would make us give strong, large steps forward. In the year 2000, we had a Millennium Institute, which was coordinated by Luis Davidovich, followed by, I don't even remember, I think 2 editions of National Institute of Science and Technology under the direction of Amir Caldeira, and then now under Belita Coelho. Throughout these 20 years, definitely our community has grown, especially qualitatively. I am sure that if you compare the science we did and the impact we had before these institutes, we've made huge progress. So in a sense, that would be one of the reasons for creating a FAPESP program, that bringing this kind of community together is useful. Now, the community in the state of São Paulo is already very well connected. And one of the reasons why Marcelo Terra Cunha is part of the organization of this effort is precisely because he put together a network called Spin-Off Qubit in the state of São Paulo, aimed at formulating a project, a thematic project, but bringing together a lot of people who were not interacting, who were not collaborating scientifically. So within the community, we already have that sense of working together. What I think is a little different here, and which is why the world is investing in these quantum initiatives, is the fact that the science that we are developing has the potential for quite disruptive technologies. And in Brazil, we have this familiar feeling that we can follow the science, we can be competitive in the science, in the academic science, and we are, even though we're not a huge community, we are. But what we're doing in our labs is not transferred to the private sector. And so we feel that the joint appeal of bringing together the private sector with the promise for the generation of near and midterm quantum technologies will, on the one hand, enable this transfer, enable economic benefits, which we would like to estimate following the procedure of the Australians, for instance. And on the other hand, bring people from related fields, magnetism, some fields, some quantum materials, things that are being studied at the synchrotron, who are not involved or not directly involved with quantum information science. We feel that those people will essentially join this effort, and that will make better science as well. So in a sense, it's not so much destined at the scientific community of this field per se, but if we do generate technology here, we will definitely have better science, and if we have better science, we will have more technology. So this is the kind of effect that I'm expecting. So it may not be exactly the traditional, the same origin of the other programs, and maybe Brito can comment further on that.
Should I comment now?
I only see now Thiago has raised his hand, so I don't know.
Maybe we can listen to Thiago.
Yeah, okay. Maybe I can just like put a little bit more of questions than answers on the table. Because I see that it's very different to have an initiative like CNPen or CIRRUS, which is a sort of like a public purchase, where you put like a problem, you say that you have to construct a huge infrastructure, and with then you join or you make calls for not only scientific but also private sector community to make that effort to go forward. And this seems to me very different from the initiative and the way that Brito describes that the other programs were. And I think, and that's like maybe like one of the things that I'm trying to understand here, or to try to put the point here, is that the quantum initiative, it doesn't seem to be neither one of them, and that seems to be good and bad at the same time, because we need some sort of drive to bring people together, but we cannot be like we cannot aim for a big purchase or a big like buying a computer, a quantum computer. We cannot say that we are doing that after 5 years. So I think that's the unique thing about this program, as far as I understood from the white paper, of course, and speaking to people, which is challenging. Because there's one thing that there's also in the white paper, which I think is very important in the case of quantum initiative, which is the awareness of the population. Because unless we make people aware that this is something that's happening and will happen, it's very difficult to create sort of, so to speak, the market. To bring the engineers, as Felinto said, to our side is very difficult to make them if we are competing with banks. So I think that's the mix of things that I feel that this initiative has to tackle, which is not easy. I have to say, but I think that's the potpourri of things that I want to just jump in and, of course, hear some comments.
Brito, in the chat, there's actually a question for you, so maybe you could
both comment. The question there.
And
question: is the Brazilian University ready for moving up the physics, quantum, to engineering?
Better if you read it loudly, because it will be recorded on YouTube.
Okay. The question from Filippo is the Brazilian University ready for moving up the physics quantum fundamental research to an engineering focused research on quantum, I suppose? Now, that all connects to what Paulo which is the thing that it's true. You could go to a foundation and say, okay, we have very good things here, and if we have a program, we can transfer more to the private sector. But I think that there are barriers there. One of them relates to what was the person who said about engineering. I cannot see the little square here anymore, but Daniel. Yeah. His point was strong. I mean, so not having the engineering schools involved in this topic is a weakness for Brazil and for the state of São Paulo. So if you want to be better treated by the foundation, it always helps if you help them to solve some of the weaknesses. So if you have an idea or a program that promises that we are going to do 1, 2, 3, 4, 5 things and get the engineering schools to be more involved in this topic. This is a way of increasing the community, increasing the quality, because you are adding another dimension of quality, which is not only having nice ideas and relevant ideas about quantum technology, but ideas that might make those into real things, which is what engineers know how to do or should know. So that's why I was saying that there's always a necessity to demonstrate that something especially good is going to be gained out of the initiative, because the initiative causes a lot of work for the foundation, for you guys, for the universities. It normally entails spending more money, so they will want to see more results. That's why I was saying that you guys need to have a case demonstrating that you are going to do more and better. So, of course, you can have another path, which is what the person who spoke before me just alluded, which is if you would promise to build something, which is okay. I mean, the synchrotron light source is one of those cases. I mean, they went to the government with the idea, we are going to build something that was never built in Brazil. We are going to use to the maximum extent local technology, and it's going to cost so and so and last so and so years. And they did it nicely. It's one of those cases, but I'm not sure if we are in a position to promise to build something relevant in this field. We might. You guys know more about the details than I do, but I don't see it by reading what I read. And there is, my last point refers to this thing about size. Size matters in this world of ideas. The more people you have having ideas, the larger is the chance that you are going to find good ideas. And, for example, Paulo mentioned Australia. Australia publishes almost twice as much as Brazil, the whole of Brazil, not São Paulo, in topics related to quantum technology. So if you count a publication as an idea, they have 2 times more ideas than we do in Brazil. Now, if you go to São Paulo, you have to divide the number for Brazil by 2 or more than 2. So Australia is like 4 times above us in the number of ideas per year. So after getting to this point, they had some ideas that allowed them to create companies that obtain VC and so on. So I would think that our first step in which having engineers involved would help would be to have the state of São Paulo be seen by the world as a relevant hub in quantum technology. So that you guys would sit in committees, be in the organizing, or other colleagues would be in the organizing committees of high visibility conferences and stuff, more than what happens today. And we would have a larger community. That's my view of the thing at this point. With what I know, not looking into the details, which you guys do and know, but by thinking about what I learned about quantum technology in São Paulo and in Brazil in the last years.
Can I just make a... Ado Jório is...
Ado Jório and then Nicolas wanted to talk. So, Ado?
São Paulo and all the friends. I want to make a very quick comment, mostly to congratulate the initiative. Both the way you are doing it, like the important points you are picking and the strategies, and of course the main topic, which is quantum information. Everything makes me really happy to see this happening in Brazil. Okay, the way I believe things are going in the world is not only about is Brazil, is São Paulo able to make something sound, something really important out of quantum technology or anything. You know, when I talk to most people around the world and people in big companies like IBM, etc., my feeling is that nobody knows what is tomorrow. Nobody knows what is the coming technological revolution, but everybody knows something will come. It's a kind of necessity. It always happens. It happens in cycles. And what everybody's doing is getting prepared. So I'm very happy that Brazil is getting prepared on this field, because I believe this field is very important. It will be very important for the countries that will be protagonists, and of course we'll have a healthy society in the coming 50, 100 years. So I'm happy that you guys are doing it, and of course if I'm able to help at any point as an outsider, I'll be very happy. Okay, so congratulations to you guys.
Nicolas? Thanks, Adu.
No microphone, Nicolas.
Microphone.
Yeah, sorry. I thought I did activate and it didn't work. But I'm saying just a quick comment, because then I will have to leave. But I very agree with what Amit said. And I think it's important that you are recognized as a well-known quantum hub. And this is what everybody is doing around the world, is trying to build a hub so that people look around and say, oh, here, something is happening. I want also to comment on about the notion of ideas. And for my experience and what I've seen around in France, a company is about two things, about ideas, but it also, and I think it's as important, about people. And many companies, for instance, after a while, they sell something which was not originally what was sold, while the people are still there. And why does it work? Because you have the good people around the table. And this is very, very important. And in quantum technologies, what we have seen in France is that a few years ago, let's say 5 years ago, there was quite a burst of startups which have been created. And now we have built up many tools to help people to create startups. And still, I find that the rate is not increasing, actually going down a little bit. And from what I discussed with some colleagues, well, it's always hard to know. This is never have a simple answer to everything. But I think definitely teaching is a key point. And as you raise the point about engineers, we need to develop current curricula about quantum technology. When you speak to big companies, they complain. Like Microsoft or Atos, which is a software company in France, they have a group of quantum technologies inside, and they have a very hard time to hire people. And if they have hard time to hire people, of course, we have a hard time to find people to develop startups. So teaching quantum technology to bring people there, I think, is definitely important. We are trying to do that in France. It's not something people do alone. So we try to collaborate with as many people as possible. And yeah, obviously we can speak together about that. That's really something which I think is very important. Okay, that was about I think important comments.
Can I ask one thing just before Marcelo asks his question, because Nicolas is about to leave us? Would everybody who can open their camera so that we can make an image of all of those present, or more than one image? Because yeah, you don't all fit on one screen. So if you can just wait a little bit there. One more. Thanks. Okay, Marcelo and Nicolas, thank you very, very much, and thank you for staying so late.
Thanks a lot for the invitation. It was very interesting, and yeah, good luck, good continuation. See you.
Merci. Au revoir.
No, what I wanted to say is more of a comment rather than a question, which is that I heard Brito mentioning a couple of times about the size of the community and the apparent lack of volume to produce initiatives like that. And I'm going to say that, like, I disagree with him. Like Paulo mentioned, the Instituto do Milênio, the first one began in 2001. As a result of this Instituto do Milênio in 2004, we had, and I guarantee you that we had, enough qualified people in Brazil to make patents on quantum cryptography. Why we didn't do it? Why we didn't develop a quantum cryptography company in Brazil is probably related to the lack of initiatives like the one that you are doing now. Maybe a little bit, maybe some other things, but like certainly initiatives like that could have helped. Quantum cryptography now may not be the new goal because it's already well established and so on. I don't know. Maybe it is still, but if we had it in 2004, we certainly have now because we have only grown since then. So I'm not sure that like volume is the biggest problem here. Probably the lack of initiatives like this one is much more serious. So in this sense, it's also to congratulate the initiative and say that like good things can happen because of that.
Thanks, Marcelo. Pierre, you wanted to say something?
Yeah, well, I did. And I've been thinking about this. Well, first of all, thanks. I'd like to thank everyone involved in taking the bull by the horns and trying to make this happen, because it sounds like a crazily complicated thing to get off the ground. And I hope you succeed. But what I was thinking about is that maybe we've heard a lot about startups, and this is really nice, but maybe the focus should be on passing the message that, I mean, sure, quantum technologies are becoming a critical part of the world, but passing the idea that if you make research in this area a priority, the startups will come as a consequence, because the quantum technology startups that I know of are consequences of research. Like, for instance, people that wanted, you probably know Pascal Senlar, and I mean, for sure you know Andrew White, and they wanted to make really good single photon sources for their experiments. And then they decided, why not sell them? And they made a startup company for this. And Peter Lodal also made a startup company for selling single photon sources. And then you have people working in Basel and working with NV centers and studying quantum sensing, another startup. But if we start by discussing how these startups will start to exist, and not focus so much on telling, look, we really need focus on this research, I'm afraid it could be seen as a hammer looking for nails instead of, I mean, it's just my feeling. I don't know how this could be perceived by FAPESP or by the industry, but I feel that perhaps, like saying, look, we have competent people, we have good ideas, and if we let research in this area flow with a bit more priority, or whatever can be arranged with the funding agency, then it is very likely, and then point to examples around the world, that this will percolate to the industry and to society as a whole. Right.
That's easy. Marcelo.
Martinelli first.
França. That was the first one to have these raised hands, at least.
Yeah.
Okay.
Go.
Okay, so it's me. Okay.
Martinelli.
And so it was Marcelo França. So, yeah, catching up the talk by the mention that Pierre-Louis made. In fact, we're hammers looking for nails, and as you mentioned, maybe he's fine. Something that's we can now is look for the nails to bring together to this program. Science of life seems to be another subject that could be interesting. Hans is involved in some measurements, was involved in some measurements for weak magnetic fields involving scalp of people. And Vanderlei has good experience on top of that. I know Marcassa has worked on top of that as well, involving programs in biology. And in fact, we have Embrapa, another an agrotech company on top of that. So maybe in the initiative, we should think about nails to bring together and add up on top of that. Medical would be an interesting point. Another question would be, okay, same direction, a question of energy. What could the knowledge that you have from quantum problems help in questions of harvesting energy or processing it in a more efficient way? So, okay, we have a good deal of different kind of hammers or tools, and we need to bring these possible applications together in the initiative. So suggestions.
Let us hear Marcelo and Pierre again, please. Marcelo's França now.
Marcelo.
França.
Okay, so let's Pierre first.
Yeah.
Okay, so first, the agriculture idea I found very interesting, and it's sad because Aldo Jorio left, but I think he already had some works on this, on doing soil analysis using Raman spectroscopy. But and I already talked a bit about this with Fred about the gravimetric sensors. And I mean, this has application in the oil industry, and the oil industry has a quota of money they have to give to research. So this is, if we can get quantum to the oil and gas industry, we could apply for A&P money. And when you mentioned medical, this year I was, the good thing about everything being online this year is that you can attend conferences in Singapore with the only inconvenience of staying up late. And in Singapore, they had this roundtable about, it was a bit about building quantum internet, but also quantum cryptography. And they discussed the necessity of quantum cryptography now, even if there isn't a quantum computer to break regular cryptography, because some types of data are attractive in the sense of steal them now and decrypt whenever you can, and they're still valuable. And this means government secrets, but it also means people's genetic data and medical records. And so apparently Toshiba is working with hospitals in Japan to encrypt data using quantum cryptography to guarantee. I mean, well, we have to see about how much of this is just for show and how much of this is really useful to protect the data. But that is an application that I think we shouldn't. Even though quantum cryptography is more developed than the rest of quantum technologies for now, I personally feel it would be a pity to say, well, that's done. Let's buy modules from ID Quantique. And I mean, I know that in principle, it could work like this, but we could still try to get our own solution to this problem. Or, I mean, good. I wouldn't count out quantum cryptography. That's what I would say.
França?
Okay, Marcelo França kept his hand on. Just two last remarks on top of what Pierre mentioned. A curiosity that comes to my mind is that is gravimetry interesting only for oil company or for investigating other kind of ore? And,
yes, you're absolutely right. Vale would be interested also, and
so anything that you want to have a good idea of what's buried before beginning to dig or taking some stronger effort to investigate. And that comes to my mind another quote that capitalism lives on creating needs. So that sounds like the entrepreneurship stuff. So that's the hard part, creating a need. So
yes, one of the parts that we really see as our mission here is really to make this catalog of interesting applications of quantum technology for someone to do. We are not only looking for what we as individuals can really be the ones doing the things. We really believe that it's important to make this roadmap, as we are calling, because we do believe that many players that are not aware of this can be important players, as Harry just gave the example in the detectors for the synchrotron. So, and these will attract people from engineering, these will attract people from computer science and whatever. So those specific applications, we essentially have all that were mentioned here in mind, but it's always good to include and to raise them again. And we really want your help in doing exactly what you are doing now, suggesting more and more topics. And of course, in some moments, we'll call some of you to help in a little bit more details on this. But of course, not to the level of doing the job itself. We just want to make a very good roadmap in order to induce these top to bottom initiatives. Okay.
This comment that was...
Can I just quickly? Yeah.
Yes.
Because you were talking again about the engineers, and that reminded me that I'm part of the outreach committee of the National Institute for Quantum Information. And we got news that there was this group of undergraduate students that were starting to do scientific communication, talking about quantum information, and they contacted Liliana, and she talked to them. And one thing that struck me was that they weren't physics undergrads. They studied engineering and computer science. Some of them in ITA, some of them in Rio, and maybe I don't remember the other one. But so there is already this interest in the engineering community, and maybe they just don't know how to approach us about this, who to approach, and how to talk, because we unfortunately have the bad reputation of not being friendly to engineers. And as I said, I wrote when Daniel Felinto mentioned it. I watched at Clio, during Clio, there was this panel about quantum internet and how different countries were approaching it, and even the US, and there was an engineer that talked about the US wanting to use the fiber optics network as a start, so as to not have to make a new network. And what he made abundantly clear to the other members of the panel that were physicists was that the engineers wanted to be heard about these discussions. So especially if we go into quantum communications, there are engineers that understand much more about how classical communications work over networks than we do in the practical sense. And it would be very good to talk to them. I mean, for sure, like Gustavo and Thiago and also Felipe, myself, we have contact with people from the electrical engineering department that are already in this interested in classical communications. And so we could maybe talk to them about this and to establish a link. And for sure at USP and UNESP, we could see to that as well.
Pegues.
Oi, Paulo. Você está me ouvindo?
Estamos todos.
Bom, eu gostaria de inicialmente agradecer ao convite.
Wait a minute. I think we were still in English.
Oh, yeah. Right. Sorry. First of all, let me thank the organizers or whoever sent me a message inviting me to participate. I've been here for the whole day, as you've probably seen, trying to hold my tongue for a while. I'm certainly an outsider to this community, even though early on in my career I did some work vaguely related to what could be called quantum communication and entangled pairs, short noise, and things like that. Now, I've been following all these discussions, and as I said, I'm here as an outsider, so I'm making a disclaimer now, right? And I think when people invite outsiders, that because they want to hear some comments, some criticism, maybe some of the criticisms are not, the ones that you want to hear, right? So I will take this view, right? That I'm just going to speak up and then say what I'm seeing, right? Of course, I'm not in this community, but I have colleagues and people that I know and interact with that is part of the community and work in related areas, right? So upon receiving this, the link, I read the white papers, and I even discussed the white paper with some of my colleagues and in other countries even, because I was just trying to participate in a sort of meaningful way, right? So I think it's a great idea. It's a fantastic initiative, right? And get all these people involved and to discuss something that is definitely, something important in the world right now, right? However, and then of course I should make a joke here. Whenever you say you should disregard whatever was said before the however, right? But that's not the case. As I said, I'm trying to be constructive here. And I'll actually point to what Brito already mentioned, right? Which is, are we, and I say we, meaning the community, ready to ask the tough questions, about the community, right? And by that, I mean what Brito already mentioned, and I've been thinking about for a while. Are we really good enough? Or do we have good enough people, A plus people, A minus, B plus, B minus people, to actually pull this through? And I think that's actually a very tough question. It makes people uncomfortable when I could see whenever Brito mentioned that, well, I don't see that, this community has enough, he said, or something to that effect, enough impact internationally to be discussing this kind of thing or something like that, right? So I think, it's an important comment, and I sort of share this kind of view because I'm always very tough on myself. When we all publish our PRLs, PRXs, and nice papers, but why is that maybe we don't really have the impact that we think we should have, right? And I think those are questions that we should consider, especially in a small group like that. I agree with, I think it was Marcelo who said something about the volume, right? It's not the size of the bunch, but it's the quality and whether you can actually deliver things. Of course, if you have a big pool of great people, it's, the more the better, but it's certainly important if you have a critical mass. So the question is, are we relevant enough to actually come up with, some good ideas that could be carried through and eventually, upon starting a startup, being able to actually deliver a product, a competitive product, be it in whatever we choose to, right? It could be an agri-business, something that would be relevant to us. I think also Marcelo pointed this out at early on in the morning sessions, right? That it's something that maybe could be, the idea would be to be more focused, right? Because I have to make this disclaimer. I was always a bit skeptical of, large-scale projects, and I never really, for instance, participated in any of these Millennium or whatever you call them institutes. And of course, the Quantum Info, quantum computing one is certainly one of the best, with many important outcomes, right? But I think now we're talking about a different thing. Now we're talking about a smaller group of people that really are trying to put something together, maybe deliver something. that would maybe impact our economy, or maybe even other economies abroad, right? So I think, I just wanted to say that I think we have to be able to ask the tough questions, put together a board, an advisory board, or whoever that would do some kind of evaluation at some point that would actually be criticizing the group harshly and not in a pejorative way. But you should not ask your mom whether you're a good singer, right? Your mom may think, my mom thinks I'm a great guy, right? But that doesn't mean anything. If she thinks I'm a great singer, I may realize when I go to a karaoke and start singing that people throw tomatoes at me, and then I realize I'm not that good. So I think evaluating committees and advisory boards are extremely important, and they have to be very diverse, and they should not be so many, so much, so much, maybe connected to the group, because from outside looking at what we're trying to do in Brazil, it's always very easy to find people say, yeah, those are Brazilians, Caipirinha, Carnival, and then they say, oh, it's great that they're doing quantum technology. But you want to be seen as a competitive group, right? I'm very proud, actually, when I visited some labs, some groups abroad, that people hide things from me, right? Because you view this competitive, right? And I think that's actually one thing I would like to share with you, is that I think this is something we should always strive for, to be viewed as very competitive. And people want to see blood in your eyes in the sense that you are after something big. So this is my 2 cents that I wanted to share with you. Thank you very much.
We have 2 more hands raised. I'm not sure Marcelo França is for real now, but I would ask people to be very brief because attendance is dropping. So Pierre.
Okay, sorry, that's the bad side of letting me talk. I don't stop. So I'd like to address, well, first, just a suggestion about topics. New materials for quantum technologies is something we should think about. And then talking about what Egis just said, and the question of why aren't we competitive? And I think that's something that maybe wasn't said enough, and this connects also with what Brito said about these chairs and getting people to come. But at the same time, I'm honestly skeptical that many people would come, because it's hard to get Europeans, for instance, to agree to come and stay more than a week or 2. So that's, but not talking about the big shots, but even being able to attract and maintain good foreign students, because the other groups have access to a much larger sea of human resources than we do, because even our students go out to these groups. So we should think about this, and it's not easy at all, and it's not a problem that maybe we can solve, because it involves the internationalization of the universities and giving classes in English and whatnot. And also, just to be very brief, there is a problem in particular to the experimentalists about access to infrastructure and to logistics, because probably many of you already had the feeling of reading a paper or visiting someone and saying, I thought about this 4 years ago, but then you cannot do it because you don't have students. You cannot buy the material. If you try to buy, it arrives 2 years later, and you don't have access to the facilities, which are sometimes right next to the MIT and not next to us. We do have facilities here, but they could be improved. And so maybe a bit of the talk with FAPESP could be in that sense, to try to improve the fabrication facilities we have, and also to come up with a way to fast track logistics for research. I mean, this would be great for everyone, but since we're talking about prioritizing, because really, if we want to talk about being competitive, I feel it's hard in experimental in the experimental field without attacking logistics, fabrication, and also being able to better recruit students and postdocs. Thank you.
Is Marcelo França around?
Yeah, yes, I am, Paulo. I have to apologize for the... actually, last time I should have lowered my hand after I spoke, and I forgot to do it. So my arm's a little bit tired right now, but this time I did raise my hand, and thank you for giving me the opportunity again. Just a quick remark about what Carlos Egues said, which is it is true that we need to ask the tough questions on ourselves. It is certainly true, but we should also not be afraid of giving the right answers. And if the right answer is that we are capable of doing it now, we should pursue the right answer. And I think that one thing that we lack in Brazil, and that is abundant in the United States for a huge number of cultural reasons, is that they are very naive on believing that they can do whatever they feel like doing, whatever they want to do, whatever they imagine doing. And we take exactly the opposite approach. We are always like, well, maybe we lack enough qualified people, maybe we lack students, maybe we lack this or that, infrastructure. And Pierre is starting to laugh, I see. He's a good friend, and I'm saying this to make him laugh as well, because he needs it today, as far as I understood. But we have to be brave enough to also give the positive answers to these tough questions and say, yeah, we do, we can, we maybe we won't be able to do as much as we would like to, but we should start giving positive answers. Again, I think that this initiative is a very positive answer and should be followed up seriously and seriously as well.
Okay, thank you, Marcelo. And I think...
Paulo, let me just make one comment from the guy that reviewed the India initiative. So a lot of the negative perspective that we might feel, if you go through the India's initiative and the records, everything they have registered, and I talk to people there in India working on their initiative, you will feel like you are in this meeting concerning the negativity and perspectives. Yet they are investing $1 billion on this. So I don't see that we have any challenge that is bigger than what India is facing, and yet they are a bit ahead of us in terms of getting the goal to pursue this path. It's just my comment.
Thanks, Gustavo. And I think what I would like to leave as a message to wrap up is that, sure, don't think for a moment that we are not aware of the problems that exist doing research and trying to create technology in Brazil. Those bottlenecks won't go away by themselves unless we have an attitude to remove them. This attitude was taken to build the synchrotron. It was taken to build Sirius. It's an attitude that we've proven before that we are capable of. I think we have to, as Eggy said, we have to have people criticizing. We have to have people telling us that, yeah, I'm skeptical of what you can do. Thank you. Because that's what is going to make this stronger. You were invited to a workshop for a white paper that has taken 3 months to put together, with very clear in the minds of the 6 people that are so far spearheading this initiative. There's a lot more work to be done. We do not envisage having this approved and started by FAPESP in less than a year. One of the main bottlenecks that we see, and we've seen it since the very beginning, is that we need to make an effort. And I think as a community, we do have enough people with sufficient vision to make this effort to find a reasonable number of targets that we can realistically pursue with all the conditions that we have in Brazil. Now, we talked a lot about startups. I almost shared again the slide that I had with the endorsers. We don't have to rely only on startups. There are big companies that are well established that exist. And if you want to know, Petrobras, for instance, has a quantum computing group established within the company. And they told us that among all the budget cuts that they had suffered this year, that group did not have any part of its budget cut. Okay, so we as Marcelo França very well put, we have to understand that we have strengths and we have to build on those strengths. We have to recognize the weaknesses, which a lot of people, easily point out, but we cannot neglect the strengths. In terms of making a mark, in terms of making ourselves visible, again, we were poked, okay? We didn't start this because, out of the blue, we thought, hey, let's commit maybe 2 hours a week of our time because we don't have anything better to do, and just come up with, concoct a plan to propose some initiative for FAPESP. No. Other countries, other groups in the world recognize the quality that we have in quantum information science in Brazil. We've made our marks, okay, and we are relevant. And they are asking, we're seeing initiatives everywhere. How come there's no initiative in Brazil? Okay, so our job right now is, I've learned a lot, I think, from what Brito said about growing a community. We've already had I wouldn't call this an epiphany, but the clear realization that if we want to build something which is called quantum information technologies, that we need to have engineers involved. And so from the point of view of the academic system of universities, it is quite clear that we need to involve engineers. And this, from the point of view of making better science, making better education, if we are able to bring in the engineering community and start teaching some serious quantum mechanics to those folks, that will be huge gain. I would like to mention that I have the experience of interacting with Michal Lipson's group, and through her, I'm in contact with a lot of people from engineering departments. We heard from Mian this morning. Mian was an engineering student, even though he has a physics background, he was in engineering departments. We understand the challenges, the difficulties. We don't want to propose something that is unrealistic, but we firmly believe that FAPESP can signal to our community, but to a broader community, that we need to invest in the development of quantum technologies in the state of São Paulo, because they will come, we should be ready for them, we can have an active role in developing them. And it doesn't have to be from the very beginning as world leaders, but if FAPESP doesn't do some inductance here, some, how should I say, driven effort, it's not going to happen, right? And this is what we see. We see a strong community, we see a diverse community. If we can bring it together, and especially involve engineers, we can develop technologies in the state of São Paulo that are within reach and that are of direct interest for economic purposes in the state of São Paulo. I see Marcelo Terracunha is signaling me things. Sure, our main focus is on sensors. That's where what we think at this point is the most promising. Certainly we have capabilities to develop tools for communications. And as Brito mentioned, we can also develop parts of computers, parts of quantum computers or software. And we have the expertise, the capability for that. As for the international panel, I think you heard from Brito, we are putting up what we consider an international advisory evaluation board. Yeah, mostly friendlies. But I understand that FAPESP, in order to promote or not this initiative, would also bring in an independent committee to evaluate the quality of what we're suggesting. So from all those perspectives, I think, you know, we have to take away from what we expected from this meeting is not a path which is going to be easy and which has no obstacles, right? We talked to Roberto Marcondes, right? And he spoke of several death valleys along the way. We know we will face several of these death valleys. The point is, if this community is willing to be involved in the formulation and the studies that are necessary to avoid those death valleys, we can do it. And so this is what we want. We want the community to be involved, to look forward and not be afraid of forging a path that we are capable of doing, for which we will have many shortcomings of our own, but we are confident that we can overcome. So that's what I'd like to say. I don't know if any other one of the six would like to say something. I greatly benefited from today. I learned a lot, and it's always nice to see things that we hadn't thought of before, difficulties we hadn't thought of before, but others that, yeah, we already thought about them. So
probably it's only important to reinforce that we count on them to continue on this path, that it's not something that we six will be able to do by ourselves, but we really need help. We ask and they can offer by themselves.
Yeah. So if not, then I think we should end on this note. And I thank all of you who have participated throughout the day. The recording will be available. And whatever materials or whatever suggestions you have, please get in touch with us. So thank you all.
Thank you.
Thanks, Paulo, Marcelo, for the invitation.
Bye-bye.
Bye-bye.
Bye, everyone.
Thank you, everyone.